Hey everyone, welcome to our MongoDB course. Get ready to dive deep into the world of NoSQL databases, where you'll gain the skills to work with MongoDB's powerful features, from setting up your database and managing collections to executing complex queries and aggregations. We'll also cover practical coding exercises to reinforce your learning. Plus, don't forget to check the description for a link to the GitHub repository with all the code you'll need. So, if you're eager to unlock your potential in database management, hit that subscribe button and let's get started. MongoDB is the most popular document database, and its versatility in handling data is unmatched. It's classified as a NoSQL, non-relational key-value store, making it a unique player in the world of databases. MongoDB primarily utilizes a JSON-like format for storing its data, which provides developers with remarkable flexibility and power. In this video, we will dive into the world of MongoDB, exploring its features, functionalities, and setup, along with practical code examples that will improve your understanding of this powerful database. Let's explore how MongoDB allows for dynamic changes to data structures. In our first code snippet, we define a simple user profile with just a name and age. This succinct representation showcases MongoDB's document-oriented approach, where data can be flexibly structured in JSON-like formats. Now, if we decide to enhance this profile by adding an address, we do so by simply nesting an address object within the existing document. The second code snippet illustrates this update, where we seamlessly integrate new fields without altering any predefined schema, something that traditional databases often require. This capability highlights MongoDB's schemaless design, enabling developers to adapt and evolve their data as application needs change. The straightforwardness of these modifications underscores why many developers favor MongoDB for applications that demand high flexibility and responsiveness to change. By directly updating documents in this way, developers can focus more on business logic rather than data management headaches. In this segment, we use MongoDB's shell to interact with our database effectively. First, we switch to a database named MyDatabase and create a collection called Users. This collection will serve as a repository for user profile documents, much like a table in a relational database, enhancing our ability to manage user data. Following the creation of the collection, we utilize the insert1 method to add a new document representing a user named Bob. This document includes his name, age, and a nested address object, demonstrating MongoDB's flexibility in storing complex data structures. By allowing such nested documents, MongoDB easily accommodates varying data fields without the need for a rigid schema. Next, to efficiently handle multiple user entries, we implement the InsertMany function. This allows us to add user profiles for Charlie and Diana in a single operation, showcasing MongoDB's capacity for batch operations. The ability to insert multiple documents simultaneously not only simplifies the code, but also optimizes performance, making operations on large datasets significantly faster and more manageable. In MongoDB, querying data is both powerful and intuitive, as demonstrated in our example. The first query utilizes the GT operator, which stands for greater than. Here, we are retrieving all users from the users collection who are older than 30 years. This showcases MongoDB's ability to perform conditional checks effectively with a simple and clear syntax, allowing for easy data retrieval based on specific criteria. Next, we explore a more complex query that employs the OR operator to fetch users who either meet one of two conditions, being younger than 28 years or residing in Springfield. This illustrates MongoDB's rich querying capabilities, enabling developers to refine their searches further by combining multiple conditions. By leveraging these logical operators, you can effectively filter the data according to varying application needs. This flexibility is particularly beneficial in real-world scenarios where data attributes may vary widely, and precise data extraction is crucial. These foundational querying techniques showcase not only MongoDB's ease of use, but also its power in handling diverse data sets. To optimize query performance in MongoDB, creating indexes is essential. The command to create an index on the name field in the user's collection utilizes the createIndex method. By specifying name 1, you indicate that the index should sort entries in ascending order based on the name field. This indexing significantly improves the speed of queries that search for users by name, resulting in quicker response times. In contrast, using -1 instead of 1 would create a descending index. Understanding index creation is crucial because it allows your application to scale efficiently without compromising performance, especially as the volume of data grows. Once an index is created, it is equally important to verify its existence and functionality. The getIndexes command retrieves a list of all indexes from the user's collection, proving useful for confirming that your indexing strategy is correctly implemented. Utilizing indexes wisely can be a game changer for ensuring that user queries are processed rapidly, illustrating the importance of thoughtful database design. To connect your Node.js application with MongoDB, you'll begin by installing the official MongoDB driver, which enables seamless interaction with the database. Once installed, you'll require the Mongo client from the library and set up a connection string pointing to your MongoDB instance. Establishing a new Mongo client instance is your first step toward communication with the database. Within an asynchronous function, you connect to the database and specify which database you want to interact with, in this case, my database. The next key action involves accessing a specific collection, termed users, where user documents are stored. To retrieve data, the code employs a simple query that uses the findOne method to fetch the document where the name matches Bob. This demonstrates how efficiently you can extract data with MongoDB's straightforward querying capabilities. Finally, ensure to close the connection after performing your operations to prevent any resource leaks. This sequence not only illustrates basic database operations, but emphasizes the straightforward nature of using MongoDB with Node.js. In this section, we explore MongoDB's powerful aggregation framework to derive insights from our data. The aggregation query begins with the aggregate function, which operates on the user's collection. Within this function, we define an aggregation pipeline using an array. The first stage of the pipeline utilizes the group operator, designed to group documents based on specified parameters. In this case, we use null for the id field, signifying that we want to aggregate across all documents without any specific grouping criterion. This allows us to treat all user records as a single group. The second key feature here is the calculation of the average age, achieved through the AVG operator applied to the age field. This command effectively computes the average of the ages of all users present in the collection. By the end of the execution, we gain a numerical output representing the average user age, showcasing the analytical prowess of MongoDB and its ability to process large datasets efficiently, which is crucial for making data-driven decisions. To shard your MongoDB database, the first step involves enabling sharding on the specific database you intend to use. This is done with the command that explicitly activates sharding for my database. Enabling sharding is crucial as it allows MongoDB to distribute data across multiple servers, improving performance and scalability for large datasets. Next, once sharding is enabled, you'll want to shard a specific collection, in this case, the user's collection. The sharding operation specifies a field. Here, userid is selected for MongoDB to use as the basis for dividing the data. By sharding on userid, MongoDB efficiently redistributes the user documents across different shards based on the value of that field. This leads to optimized data management and retrieval, allowing your application to scale seamlessly and handle increased loads with minimal impact on performance. Understanding and properly implementing these sharding commands is vital for maintaining efficiency as your application grows and requires more robust data handling capabilities. As we wrap up this introduction to MongoDB, it's clear that it provides a powerful toolkit for developers to create dynamic, responsive applications. Its schemaless architecture, robust querying capabilities, and outstanding scalability make it an ideal choice for a plethora of modern use cases. Diving into MongoDB means opening the door to a world of flexibility and simplicity in data management. Whether you are developing web apps, mobile apps, or big data solutions, MongoDB is well equipped to meet your needs. I hope you're excited to dive deeper into MongoDB and unleash the potential it holds for your projects. Thank you for watching. Don't forget to like, subscribe, and hit that notification bell for more awesome content on database technology and programming. Remember, whether you're building that next big application or just learning to harness the power of data, MongoDB has got your back. Happy coding! Understanding the architecture of MongoDB is key to effectively utilizing this powerful database system. Today, we are diving deep into how MongoDB operates, unpacking its components, data flow, sharding, replication, and much more. So far, we learned about MongoDB's schemaless architecture, collections, documents, and its indexing capabilities for optimized performance. Now we will cover the internal workings of MongoDB, comprehending its architecture, and why it is designed the way it is. In MongoDB, a document is represented in a format similar to JSON, which is flexible and allows for a variety of data types. The provided code illustrates a user document containing essential information: the user's name, age, and a nested address object. The use of key-value pairs provides clarity and structure, with the primary fields, name and age, appearing at the top level. Nested within this document is the address object, which further organizes related information, categorizing the user's street and city under a single key, address. This nested structure demonstrates MongoDB's schemaless nature, allowing for easy expansion and modification of data without requiring predefined schemas. The binary format, BSON, that MongoDB utilizes can effectively handle such structured data, facilitating efficient storage and retrieval. This flexibility is particularly beneficial for developers, as it enables them to swiftly adapt their data models to suit changing application requirements. Overall, this simple yet structured example showcases how MongoDB's document-oriented approach empowers developers to manage complex data relationships effortlessly. To set up sharding in MongoDB, we begin by enabling sharding on the specific database we want to distribute. This is done using the command that activates sharding for the shop database. By enabling sharding, MongoDB can partition data across multiple servers, effectively managing larger datasets and balancing the load to optimize performance. Once sharding is enabled, the next step involves defining how data will be distributed across shards. This is achieved by sharding the specified collection, in this case, users within the shop database. By using UseRid as the shard key, we instruct MongoDB to partition the user documents based on the hashed values of their user IDs. This utilization of a shard key ensures that data is spread out evenly across the shards, preventing any single server from becoming a bottleneck, thereby facilitating efficient scaling as the application's data grows. Each of these commands is crucial for maintaining a robust, scalable MongoDB setup that adapts to increasing user demands and ensures high availability. To establish a replica set, we utilize the initiate method, which is critical for ensuring data redundancy and high availability in MongoDB. In this code snippet, we define our replica set with an ID of myReplicaSet and include 3 members, each specified by unique identifiers, and the host addresses pointing to different servers. The first member, labeled with id 0, is hosted on server 1, 27017, followed by the second member on server 2, 27017 with id 1, and the third on server 3, 27017 with id 2. This configuration ensures that even if one server fails, the others still maintain a copy of the data, allowing your application to continue operating smoothly without data loss. This setup illustrates the robust architecture of MongoDB's replication feature, designed to enhance fault tolerance. The primary node, which is one of these members, will handle all write operations, while any secondary nodes will replicate this data seamlessly. The automatic failover capability is crucial, allowing quick recovery and uninterrupted services in case of failures. In this section, we'll explore how MongoDB executes an update operation using the provided code example. The code utilizes the update1 method on the user's collection to modify the data of a specific document. The first part of the method specifies the query criteria, identifying the document to update by matching the name field to Alice. This query ensures that only the intended document is targeted for modification. The second part uses the set operator, which is crucial as it allows for updating specific fields within the document without altering the entire structure. In this case, we are updating the age field to 31. By leveraging the set operator, you maintain the integrity of the document while making only necessary changes. Once the update is executed, MongoDB applies these changes efficiently, thanks in part to its write-ahead logging mechanism, which ensures that the operation is recorded in a journal before any modifications are made to the database. This approach guarantees data consistency and resilience against unexpected failures, reinforcing the reliability of operations within MongoDB. Creating an index in MongoDB is a straightforward yet powerful operation that significantly enhances query performance. In this example, the command uses db, users, createIndex, name, 1, where the createIndex method is called on the user's collection. The index is established on the name field, with the value 1 indicating that the index should be sorted in ascending order. This sorting mechanism allows MongoDB to quickly locate and access documents based on the name field, making retrieval operations far more efficient. When you execute a query to find users named Alice, for example, MongoDB can bypass a full collection scan, dramatically reducing the time it takes to return results. Proper indexing is particularly crucial in datasets with a large number of documents, as it transforms each search operation's complexity from O(n), where n is the number of documents, to O, log n, through index scans. This improvement can be a game changer for applications requiring fast read responses, making the use of indexes vital in delivering an optimized user experience. This aggregation query exemplifies the power of MongoDB's aggregation framework, where data can be processed and insights derived without extensive application overhead. In this query, we utilize the group stage, which is essential for organizing and summarizing data. Here, we group users based on their city, indicated by the id field referencing address city. This allows us to categorize all users residing in the same city together. Furthermore, we calculate the average age of users within each city group using the AVG operator, applied to the age field. This not only simplifies the calculation of average values across potentially large and complex datasets, but also showcases the efficiency of MongoDB in handling such operations directly within the database. By performing this aggregation, we can quickly extract meaningful insights, such as demographic age distributions across locations, without the need for exporting the data to external processing systems. This demonstrates how the aggregation framework streamlines data analysis efforts, making it easier for developers to leverage data-driven decisions effectively within their applications. As we approach the conclusion of our exploration of MongoDB's architecture, it's important to highlight how its design lends itself to horizontal scalability. The architecture was created with cloud computing and distributed data models in mind, making it suited for modern applications that demand flexibility, speed, and reliability. As a developer, understanding how to leverage MongoDB's architecture can significantly influence your application's performance and the ease with which you can manage data. By harnessing the power of sharding, replication, intelligent indexing, and the aggregation framework, you can build applications that not only meet your data needs, but also adapt and grow with your business over time. This design philosophy ensures that scaling does not compromise your application's reliability, allowing you to focus on development without worrying about underlying infrastructure limits. So there you have it. Today, we unpack the intricate architecture of MongoDB, exploring how its components work together to create a powerful database solution. Its flexibility, ease of modification, and strong performance capabilities make it an ideal choice for modern applications. Remember, whether you're working on startups or enterprise-level solutions, understanding the architecture is vital in designing efficient data-driven applications. As we wrap up this session, I hope you feel equipped with a deeper understanding of MongoDB's architecture and how to leverage its features effectively. Be sure to apply what you've learned today to your projects and continue to explore the fantastic capabilities that MongoDB has to offer. Happy coding, and see you in the next lesson. MongoDB's architecture is designed to meet the rapidly changing demands of modern applications, offering a flexible and efficient platform for managing data. In this video, we're diving deep into the core architectural foundations of MongoDB, focusing on how its features like collections, documents, and advanced sharding strategies allow developers to maintain high-performance applications in today's dynamic environment. So far, we learned about MongoDB's architecture, including its schemaless design, collections, documents, and indexing for performance optimization. We discussed crucial components like sharding for scaling and replication for high availability, ensuring data safety and seamless service. Additionally, we explored the wired Tiger storage engine and its transaction management, as well as the importance of indexing and the aggregation framework for data processing. Overall, we've gained insights into how MongoDB's design supports modern application needs for flexibility, speed, and reliability. Now, we will cover how MongoDB utilizes replication and sharding to enhance performance and reliability. In this section, we're looking at how to insert a document into a MongoDB collection, demonstrating its flexible schemaless design. The code provided uses the insert1 method on the user's collection to add a new document containing user information. Each document is structured as a JSON-like object, making it easy to define various fields such as name, email, age, and interests. What stands out here is that, unlike traditional databases, there's no need to predefine the structure of the document. This means that the user's collection can contain documents with varying fields, allowing for easy adjustments as application requirements evolve. For instance, if we decide to include an additional field like occupation, in the future, we can simply update that specific document without impacting others. This feature promotes agility in development, enabling faster iterations and tests of new features as requirements change. Overall, the insert1 operation is a powerful tool that exemplifies MongoDB's approach to managing diverse datasets efficiently within modern applications. To optimize query performance in MongoDB, we need to create indexes on fields that are frequently queried. The line of code you see here executes a command to create an ascending index on the email field within the user's collection. This means that MongoDB will organize the data in a way that allows it to quickly locate entries based on the email addresses. The 1 in the command signifies that the index is in ascending order. If you were to use -1, it would indicate a descending order index. By utilizing indexes like this, MongoDB reduces the need for a time-consuming full collection scan, thereby enhancing the overall speed and efficiency of read operations. When an application queries the email field, MongoDB will reference the index to quickly find the relevant document instead of sifting through all documents in the collection. Establishing indexes effectively can lead to substantial performance improvements, especially in applications with large datasets or frequent read operations. In this section, we explore the command used to add a new secondary member to a replica set in MongoDB, which is crucial for enhancing data redundancy and availability. The command rs add secondary example 27017 is executed on the primary node of a replica set to include another MongoDB server as a secondary instance. When you execute this command, you're effectively increasing your system's resilience. The added secondary member will replicate data from the primary node, enabling it to take over as the new primary in case the original primary fails. This automatic failover capability ensures that your application remains operational, even during server outages. It also allows for improved read scalability, as multiple secondary nodes can handle read requests simultaneously, distributing the load and enhancing performance. Ultimately, adding secondary members like this is essential in maintaining high availability and ensuring data durability within your MongoDB deployment, illustrating a foundational aspect of its replication strategy. In this section, we'll look at how to implement sharding in MongoDB by using the shard collection command. This command is fundamental for enabling horizontal scaling by distributing data across multiple servers, making your application more efficient as it grows. The command shard collection products category 1 is used to designate the products collection within the star database for sharding, specifically using the category field as the shard key. The shard key is crucial because it determines how the data will be divided among the shards. In this case, by sharding on the category field, MongoDB will distribute the data based on the various product categories, which can lead to improved query performance, as related data is stored together. The 1 in the command denotes that the sharding will be done in an ascending order based on the category values. Choosing the right shard key is essential. It impacts not only load balancing, but also performance and the way data is organized across shards. Once implemented, this configuration allows MongoDB to manage data across multiple servers, ensuring that each shard handles a balanced amount of data, ultimately enhancing the overall performance and scalability of your application. In the context of a sharded architecture, the visualization of how components interact is crucial for understanding MongoDB's performance optimization. The diagram illustrates the role of the Mongo's instance, also known as the query router, which serves as the intermediary between client applications and the sharded database. When a client sends a query, it connects to Mongo's, which thoroughly analyzes the request to determine the relevant shard or shards that contain the requested data. This direct routing mechanism minimizes the load on individual shards and streamlines data retrieval, ensuring efficient query execution. In a production environment, it is highly recommended to run multiple instances of Mongo's. This strategy not only enhances load balancing across queries, but also fortifies system availability, allowing for uninterrupted service even during high-demand periods or server failures. Thus, understanding this simplified interaction between the Mongo's and the shards is essential for optimizing application performance, particularly as your data scales and the complexity of queries increases. Through effective use of the query router, MongoDB can maintain high responsiveness and reliability. To check the status of the MongoDB balancer, we use the command get balancer state. This command is an essential tool in managing your sharded cluster, as it helps determine whether the balancer, which redistributes data across shards to maintain even load distribution, is currently active or not. When executed, this command will return either true if the balancer is running or false if it is inactive. Understanding the status of the balancer is crucial for ensuring optimal performance and avoiding potential bottlenecks in your system. If the balancer is disabled, certain shards might become overloaded with data, leading to slower response times and inefficient resource utilization. In contrast, with the balancer active, MongoDB dynamically manages the distribution of data chunks among the shards, enhancing overall workload balance. By regularly monitoring the balance's status, you can proactively manage your sharded environment, ensuring that your applications are running efficiently without hotspots or performance degradation. This step is vital for maintaining a robust and scalable architecture in your data management strategy. In a sharded MongoDB cluster, optimizing read operations is crucial for maintaining performance. When you execute a query that includes the shard key, as demonstrated in the first code snippet with DB products. Find, category, electronics. The query is precisely directed to the relevant shard that holds the data for the electronics category. This targeted approach significantly enhances efficiency, as it avoids unnecessary queries to irrelevant shards, leading to faster response times. On the other hand, if your query does not utilize the shard key, as seen in the second code snippet, DB products, find, MongoDB is forced to perform a scattergather process. This means it will broadcast the query across all shards in the cluster, potentially resulting in longer response times since every shard must be queried regardless of whether it contains the sought data. Understanding this distinction in querying behavior emphasizes the importance of strategically choosing shard keys to improve read operation performance and enhance overall application efficiency. As we wrap up our discussion on MongoDB's architecture, it's clear how replication and sharding work in tandem to create a robust system for modern applications. This combination not only ensures availability and durability of data, but also allows incredible scalability to handle vast datasets. With the right understanding of MongoDB's architectural foundations, you can develop high-performance applications that meet the ever-growing demands of your users. In conclusion, whether you're optimizing your collection structure, implementing effective indexing strategies, deploying replication for resilience, or applying sharding for scalability, MongoDB equips developers with the tools needed to harness data effectively. Stay tuned for more lessons, where we can explore more advanced features within MongoDB that will empower you to maximize your application's potential. Replication is a crucial component in MongoDB's distributed architecture, ensuring data accessibility and resilience to faults. In this section, we will dive into the mechanisms behind replication and sharding, exploring how they work together to provide database reliability and scalability. So far, we learned that MongoDB's unique data model uses collections made up of flexible JSON-like documents, allowing for dynamic schema design. We explored the importance of indexing for performance optimization and discussed replication through replica sets for ensuring data durability and high availability. Additionally, we delved into sharding as a method for horizontal scaling, detailing its components and how it distributes data across multiple servers. Overall, we've seen how these architectural features work together to enhance the flexibility, speed, and reliability of modern applications. Now we will talk about how replication and sharding mechanisms work and why they are vital for any application. To initiate a replica set in MongoDB, we use the rs_initiate command, which sets up a new replica set configuration. In this example, we provide an identifier for the replica set with id, rs0, establishing a clear identity for managing the set. The members array specifies the servers that will be part of this replica set. Here we include 3 servers, one primary server designated as id, 0 and 2 secondary servers with id, 1 and id, 2. Each member is identified by its id and host, which indicates where the MongoDB instance is running, denoted by the server names and pots, e.g., primary 27017 for the primary server. Once executed, this command instructs MongoDB to begin replicating data from the primary server to the secondary servers. This replication ensures that all 3 servers maintain the same dataset, enhancing data availability and fault tolerance. By setting up these members in a structured way, you lay the groundwork for automatic failover processes and the capacity to manage read operations across different servers, significantly improving the reliability and scalability of your application. To check the status of your replica set, you will use the command rs_status. This command provides critical information about the current state of your replica set, including details on each server's health and role within the set. Upon execution, the command returns a document that outlines the active status of all members. Specifically, it identifies the primary server as 1, which signifies that it is currently available to handle write operations. Additionally, the secondary servers are marked as 2, indicating they are healthy and replicating data correctly. However, if a secondary server encounters an issue and becomes unresponsive, it will be represented as 0, alerting you to the problem. This information is crucial for maintaining high availability, as it allows you to quickly identify any faults in your replica set. Understanding the output of this command helps ensure that your application continues to function smoothly by swiftly addressing any issues that may arise within the replica set. In this section, we will explore how to control read operations in MongoDB to optimize performance. The command db collection find readpref secondary is used to specify that the query should prioritize reading from a secondary member of a replica set. This capability is particularly useful in high-traffic applications where the primary server might be overwhelmed with read requests. When you employ this read preference, MongoDB redirects read queries to secondary nodes, allowing the primary server to focus on handling write operations. This not only helps to balance the load across your database servers, but also enhances the overall performance of your application. However, it's crucial to keep in mind that reading from secondaries can lead to slightly stale data due to replication lag. This means that while you may benefit from improved read efficiency, there's a potential trade-off in data freshness, since the secondary may not have the most current changes at the time of your read request. Therefore, judiciously choosing when to use this read preference can greatly improve scalability without compromising data integrity significantly. To enable sharding for your MongoDB collection, you use the shard collection command. This command specifies the collection that you want to shard. In this case, the orders collection within the e-commerce database, and it indicates the shard key that will be utilized for distributing data across multiple servers. The shard key, represented here as the customid 1, is critical because it determines how the data is partitioned. By using the customid as the shard key, you ensure that documents with the same customid are likely stored on the same shard. This optimizes data retrieval for read and write operations related to specific customers, thereby improving the application's performance. The 1 signifies that MongoDB is using an ascending order for this key, which is important for ensuring an even distribution of data. Once you execute the command, MongoDB begins to use the customid field to distribute future documents across your shards intelligently. Properly defining the shard key is essential, as it plays a crucial role in maintaining efficiency and load balancing across the sharded cluster. In a sharded cluster, the architecture is designed to efficiently manage large datasets by distributing them across multiple servers. The diagram illustrates the role of the Mongos, which acts as a query router, facilitating communication between the client application and the various shards. When a client sends a request, it connects to a Mongo's instance. This is crucial because the Mongo's interprets queries based on the shard key, directing requests to the appropriate shard that holds the relevant data. For example, if the customid is used as the shard key, the query router will ensure that the request is routed specifically to the shard responsible for that customid, minimizing unnecessary data retrieval and improving response times. This architecture not only allows MongoDB to efficiently handle a large volume of data, but also enables the system to scale horizontally. As more data is added, or as the application demands increase, additional shards can be included in the cluster. This modular approach ensures that the system remains responsive and can accommodate growth without sacrificing performance. In this section, we will explore how to check the status of the balancer in a sharded MongoDB environment. The command get balancer state is used to determine whether the balancer is currently active. The balancer is a crucial component that manages data distribution across the shards, ensuring that no single shard carries more data than it can handle. If uneven data distribution occurs, the balancer will relocate data chunks from overloaded shards to those with more capacity, thus maintaining optimal performance. By executing this command, a developer can obtain a simple Boolean response. True indicates the balancer is operational, while false signifies that it is not running. Understanding the balancer's state is vital for administrators to ensure data is effectively managed across shards, particularly in high-traffic applications where data load can fluctuate significantly. Regularly checking the balancer's status can help prevent performance bottlenecks and allow for seamless scalability as your application grows. Thus, using this command is an essential practice for maintaining the efficiency of your sharded MongoDB setup. In a sharded environment, crafting efficient queries is crucial for optimal performance. The first code snippet demonstrates how to retrieve documents from the orders collection by specifying a precise custom-ed. This targeted query directs MongoDB to only the shard that houses the data associated with the custom-ed 12,345, significantly enhancing query speed and resource efficiency. By narrowing the search to a specific shard, the system avoids unnecessary overhead of scanning irrelevant shards, thereby minimizing response times. Conversely, the second code snippet illustrates a non-targeted query that retrieves all documents from the orders collection. This approach engages a scattergather mechanism, causing the database to query every shard in the cluster. While it may yield results, this method is far less efficient, as it requires MongoDB to collect and aggregate data from all shards, potentially resulting in slower response times and increased resource consumption. Therefore, when working in a sharded setup, always use the shard key for targeted queries to ensure optimal performance and faster data retrieval. In summary, understanding MongoDB's replication and sharding mechanisms is fundamental for building robust, reliable, and high-performance applications. Replication ensures data availability through replica sets, allowing automatic failover and RED scalability. Sharding allows for distributing large datasets across multiple servers, significantly enhancing the application's capacity to handle an increasing amount of data and user load. As you design your applications with MongoDB, it's crucial to consider how these features fit together to provide a seamless user experience while maintaining data integrity and speed. By leveraging replication and sharding correctly, you can build powerful applications that stand resilient against failures and scale effortlessly in response to demand. Stay tuned as we continue to explore more advanced features in MongoDB, offering more tools and techniques to maximize the potential of your database-driven applications. Mastering the art of MongoDB development can be challenging and requires more than just an understanding of the core concepts and syntax. One key to becoming proficient lies in familiarizing yourself with the extensive range of developer tools that MongoDB offers. In this tutorial, we will explore these tools in depth, look into their functionalities, and see how they can make your MongoDB development process smoother and more efficient. In this example, we use the MongoDB shell to insert a new document into the employees collection, showcasing how straightforward it is to manage data within a MongoDB database. The command starts with DB, employees, insert one, where DB refers to the current database context and employees is the specific collection we're targeting. The insert one function is designed to add a single document, which is represented as an object containing various fields. Each field describes a characteristic of the employee, such as first name, last name, email, department, and salary. By passing in this structured object, you illustrate the flexibility of MongoDB's schema design, allowing you to store varying types of data as required. For example, you could easily adjust the fields based on your application's needs, whether adding new ones or omitting unused attributes. This command not only populates your collection with meaningful data, but also empowers developers to build dynamic and adaptable applications by taking advantage of MongoDB's capabilities. To retrieve documents from a collection in MongoDB, the shell provides some straightforward commands. The command to fetch all documents from the employees collection is simply db employees find. This retrieves every document without any filters, allowing you to see all employee records stored in that collection. If you're working with a larger dataset and need better readability, DB, employees, find, pretty, enhances the output format. It formats the results in a more visually appealing manner, making it easier to scan through multiple documents by adding indentation and line breaks, particularly useful when handling numerous entries. Furthermore, the MongoDB shell's ability to execute a JavaScript file is a significant feature for developers. By using load, path/to/your script, JS, you can run predefined scripts containing a series of commands or operations. This approach not only saves time, but also keeps your workflow organized, enabling you to maintain a consistent record of database operations while allowing for easier updates and modifications to your scripts as your development needs evolve. Let's shift gears and discuss MongoDB Compass, an intuitive graphical user interface designed to simplify database management. Compass allows you to visually explore your data, making it accessible even for those less familiar with command-line interfaces. When you launch Compass, you can connect to your MongoDB instance by entering the required connection parameters, such as the URI for your database. Once connected, you will see a clean interface with a tree-like structure representing your databases and collections. This visual representation makes it easy to navigate through your data. For example, if you want to query data, Compass provides an intuitive query builder where you can point and click to define your search criteria. Let's say you're interested in finding all employees in the HR department. You can construct your query visually and see the results presented in real time. This approach saves time and reduces the learning curve associated with writing raw queries. One of the standout features of Compass is its aggregation pipeline builder, which simplifies creating complex data transformations. You can visualize each stage of your data processing and see how data flows through the pipeline. The interface updates live, providing immediate feedback about how each stage affects your data. To manage your MongoDB Atlas clusters effectively, you can utilize the MongoDB CLI to execute various commands directly from your terminal. One essential command is MongoDB Atlas dbuses list, which retrieves and displays information about all users within your configured cluster. This command is crucial for maintaining security oversight as it provides details regarding user roles and database access permissions. By regularly checking this information, you can ensure that your cluster's security settings align with best practices, minimizing the risk of unauthorized access. Another powerful functionality of the CLI is the ability to import data seamlessly into your collections. The command MongoDB Atlas import JSON file path / your file, JSON collection employees quiet, allows you to import a JSON file directly into the specified employees collection. This feature is invaluable for developers who need to populate their databases with initial data or update existing records, as it simplifies the process of transferring data from external sources into your MongoDB environment. The use of the quiet flag further ensures that the command runs without outputting unnecessary logs, making your workflow more efficient. As we explore these tools, it's also important to keep best practices in mind to optimize your development workflow. First, always secure your connections using appropriate authentication and user roles. Regularly update tools like MongoDB and Compass to benefit from the latest features and fixes. Backups are essential, especially before significant changes. Use tools like MongoDB to create backups of your data. Using version control for your scripts and queries is another great practice. Tracking changes helps maintain a history of your database interactions, which is invaluable for audits or debugging. Moreover, when utilizing tools like Compass or MongoDB, familiarize yourself with the help commands and documentation. These resources offer critical insights into commands, syntax, and operational tips that can elevate your efficiency as a developer. In summary, the developer tools provided by MongoDB are designed to enhance your experience, making database management, querying, and operations much more straightforward. By leveraging the capabilities of MongoDB, Compass, and the CLI, you can optimize your development process and build robust applications with confidence. The journey into MongoDB development may be challenging, but with the right tools and practices, you can turn complexity into simplicity, making your job as a developer much easier. With that said, I hope you found this exploration into MongoDB developer tools enlightening. From mastering the shell to navigating Compass and leveraging the CLI, you are now equipped to tackle your database challenges more effectively. Stay tuned for our next session, where we will dive into connecting to MongoDB and explore driving MongoDB interactions with your favorite programming languages. The MongoDB for Visual Studio Code extension transforms application development within VS Code, offering substantial features that enhance your productivity and make working with MongoDB smoother and more efficient. Today, we're diving deep into this extension to uncover its capabilities, guiding you through everything from setup to executing queries and managing your databases. So far, we covered the essential tools that enhance MongoDB development, including the MongoDB shell, Compass, and the CLI. The shell allows for direct database interaction and efficient CRUD operations, while Compass offers a user-friendly interface for visual data exploration and query building. We also emphasize the importance of best practices to optimize workflows, such as securing connections and using version control for scripts. With these tools and practices, developers can simplify complex tasks and improve their overall productivity in MongoDB. Now, we will cover how to leverage the MongoDB extension for Visual Studio Code to elevate your development experience even further. First, let's talk about the installation process of the MongoDB extension for Visual Studio Code. It's straightforward, just like your favorite kitchen gadget that makes cooking a breeze. Begin by opening Visual Studio Code. From the sidebar, navigate to the Extensions view by clicking on the Extensions icon, or simply press Ctrl+Shift+X. In the search bar, type MongoDB for VS Code. Once you find the extension, click the Install button. Just give it a moment to get set up, and voila! You're now ready to start exploring MongoDB within your favorite code editor. To connect to your local MongoDB instance, you'll need to use a specific format for the connection string. This string is essential as it directs your application to the MongoDB server you want to connect to. In this instance, the connection string is MongoDB//localhost 27017. The MongoDB // indicates the protocol, confirming that it is a MongoDB connection. Following this, localhost points to the MongoDB server's location, which in this case is your local machine. It signifies that the server is running on the same device you are using. The 27017 at the end denotes the default port number for MongoDB, where the server awaits incoming connections. Using this connection string is similar to having the exact address of a coffee shop. It tells your application the precise location it needs to access to interact with your database. By entering this string into the prompt, you create a dedicated link between your development environment and your local MongoDB instance, enabling you to explore and manipulate your data effortlessly. Now that you're connected, let's explore how to navigate through your databases and collections. On the left sidebar, you'll see a new MongoDB icon. Click on it, and you should see your databases listed. Expanding a database reveals its collections. It's laid out similarly to a file explorer, making it easy to find what you need. Suppose you want to view the documents in a collection. Just click on the collection name and select Find Documents. The results will appear in a new tab within VS Code. This feature allows you to visually inspect your data without needing to write out queries every time, which certainly saves you time and energy, like using a coffee maker instead of brewing over a fire. To effectively query your MongoDB database, it's important to understand the structure of your queries. The first query is aimed at retrieving all documents from the collection where the department is HR. This is a straightforward filter, allowing you to focus your search on a specific group of employees within your organization. By specifying the department, you can quickly isolate the relevant data you're interested in. The second query builds upon this foundation by adding an additional condition. Not only does it filter employees from the HR department, but it also narrows down the results to those with salaries exceeding $50,000. This use of the GT operator introduces a level of complexity that demonstrates MongoDB's powerful querying capabilities, enabling you to extract precisely the information you need. Such filtering is particularly useful for analyzing employee salary data or generating reports based on department performance. Overall, these queries illustrate how MongoDB allows for intuitive and flexible data retrieval, helping you efficiently manage and analyze your database's information. Inserting a new document into your MongoDB collection is a straightforward process that requires structuring your data in JSON format. The given code represents an employee record, encapsulating essential information about a person you would typically manage in a database. Let's break it down. It starts with the employee's first name as Jane, followed by her last name, Smith. This format highlights how you can represent each attribute of the employee clearly and concisely. Next, the email field contains a unique identifier, ensuring that each employee can be contacted directly. The department field categorizes Jane as a member of the IT department, allowing you to filter or sort employees based on their roles. Finally, the salary field assigns a numerical value, reflecting Jane's earnings, which could be used for various calculations, like payroll management or budget analysis. By structuring your data this way, you not only maintain clarity, but also set the stage for effective data manipulation and querying in future operations. This approach is essential for managing documents efficiently in your MongoDB database. In this section, we will explore a simple yet powerful aggregation pipeline in MongoDB designed to calculate the average salary of employees within the HR department. The first stage of the pipeline is the match stage, which acts as a filter, ensuring that only documents belonging to the HR department are considered in subsequent operations. This is critical for narrowing down the data set to the relevant records needed for our calculation. Next, we move to the group stage. Here, we gather the filtered documents and group them together. In this case, we want to calculate an average rather than identify unique values, so we set the id to null. This tells MongoDB that we are aggregating all matching documents into a single result. The magic happens in the average salary field, where we use the AVG operator to compute the average of the salary field across all documents in the group. By executing this aggregation pipeline, you gain valuable insights, such as understanding salary distributions within a department, which can aid in making informed decisions regarding budget planning and human resource management. This showcases the power of MongoDB's aggregation capabilities right within your development workflow. To create an index in MongoDB, you would set up a JSON object that specifies the index's key and its order. In this case, the index is defined with the last name field, which is critical for improving query performance when you frequently search for employees by their last names. By specifying 1 next to the field name, you are creating an ascending index, which organizes the data in a way that optimizes retrieval. This arrangement allows MongoDB to locate the relevant documents quickly, much like how a well-organized library makes it easier to find a specific book. Once this index is in place, every time you perform a query that involves the last name, MongoDB will leverage this index to streamline the search process, significantly reducing the time it takes to retrieve data. This automated optimization is key in large databases, where efficient data access can greatly enhance application performance. Overall, establishing indices is a foundational practice that ensures your database operates efficiently and effectively, allowing your application to scale seamlessly as data grows. In this section, we will explore how to create a new user in MongoDB, focusing on the necessary JSON structure to define user access and roles effectively. The JSON begins with specifying the target database for the new user. This is crucial because it ensures that the user will have permissions within the appropriate context of your project. Following that, the username and password fields define the user's credentials for authentication. The most important part of this JSON structure is the roles array, where you specify the various roles assigned to the user. In this case, we designate the role of read-write, which allows the user to both read from and write to the specified database. This role is particularly useful in team settings, as it facilitates collaboration by ensuring that team members can access and modify the necessary data to perform their tasks. By utilizing this structure, you're ensuring that your database permissions are tightly managed, enhancing both security and efficiency in your development workflow. Proper user management is an essential best practice in maintaining a robust and collaborative workspace. This code snippet demonstrates how to define a schema for an employee in MongoDB using Mongoose, a popular ODM, Object Data Modeling, library for Node.js. First, we import the Mongoose library, which provides the functions necessary for interacting with our MongoDB database. The core of our code is the employee schema definition created using new Mongoose schema. This schema outlines the structure of the employee document, detailing the fields that each employee entry should contain. Specifically, we have fields for first name, last name, email, department, and salary, each with specific data types and validation requirements. For instance, both first name and last name are strings that are required for each document, ensuring that we don't create employee records without these essential details. The email field is a string that must be unique, preventing duplicate entries, which is crucial for maintaining data integrity. Finally, we export the model using module exports, allowing us to use our defined schema in other parts of our application. This setup not only streamlines data manipulation, but also promotes consistency across employee records, making it easier for your team to collaborate effectively. Lastly, let's talk about troubleshooting and supporting features. The MongoDB extension comes with integrated error reporting, helping you diagnose issues on the fly. If something goes awry with your queries or connections, the built-in logging can provide you insight into what went wrong. This functionality can be a lifesaver when debugging database interactions. Imagine you executed a query and get an error that says database not found. The error log will typically guide you toward resolving the issue quickly and efficiently, helping you maintain your focus on building awesome applications rather than getting bogged down in technical snags. As you can see, the MongoDB for Visual Studio Code extension equips you with a powerful suite of tools that can transform your development workflow. From connecting to your databases, running queries, managing document insertion, and aggregating data to handling user roles and permissions, this extension makes it easier and faster to work with MongoDB directly in your favorite code editor. In summary, integrating MongoDB into your development environment through Visual Studio Code allows you to streamline your processes, reduce complexity, and improve overall productivity. This combination is akin to having a Swiss Army knife at your disposal. Everything you need is right there, making development faster and more efficient. Now that you have a comprehensive understanding of the MongoDB extension for Visual Studio Code, I encourage you to dive in and start experimenting. Working hands-on with these tools will cement your knowledge and turn you into a MongoDB wizard, ready to take on any challenge that comes your way. Happy coding! In the world of database management, MongoDB stands out as a powerful, flexible, and scalable NoSQL solution. This unique positioning allows it to cater to diverse business needs, from rapid data retrieval to the management of large datasets across extensive networks. Today, we'll dive deeper into connecting with MongoDB, exploring different programming languages and methods, while providing code examples and detailed explanations along the way. So far, we learned about the MongoDB extension for Visual Studio Code, which streamlines development by allowing easy installation, connection to databases, and management of data. We explored various features such as querying, inserting documents, and utilizing the aggregation framework to perform advanced operations. Now we will talk about how to connect MongoDB with different programming languages, including Node, JS, Python, PHP, and Ruby, highlighting each unique connection process. Now, let's delve into the JavaScript code used to connect to a MongoDB database with Node.js. Initially, we import the Mongo client from the MongoDB driver, which is essential for establishing a connection to the database. The connection string must be properly configured with your MongoDB credentials and the server address. After creating an instance of Mongo client, we define an asynchronous function named run that handles the connection process. Within this function, we utilize a try block to attempt to connect to the MongoDB server, ensuring that if any errors occur, they are gracefully handled. After a successful connection, we access the productions database and the movies collection. We set up a query to search for a specific movie titled 200 meters, demonstrating how to retrieve documents from the collection. The result of the query is then logged to the console, providing immediate feedback on the operation. Finally, the finally block ensures that regardless of the outcome, the client closes the connection to prevent resource leaks, illustrating good practices in error handling and resource management in asynchronous programming. In this section, we'll delve into the Python code that connects to a MongoDB database using the PyMongo library. First, we import the Mongo client class from the PyMongo module, which provides the means to interact with our MongoDB server. By creating an instance of Mongo client, we establish a connection to the server using the specified connection string that includes the username, password, and server address. Once connected, we access the specific database named Productions and then narrow down to the movies collection where our target data resides. The code demonstrates a straightforward querying process by defining a query dictionary that specifies the title of the movie we want to retrieve, in this case, 200 meters. Using the findOne method, we efficiently fetch this document from the collection. Finally, we print the result to display the movie's details. This structured approach illustrates how developers can effectively interact with MongoDB in Python, leveraging its ease of use and Python's clear syntax for database operations. In this section, we will look at how to connect to MongoDB using PHP, which is facilitated through the official MongoDB library. The first step involves using Composer to install the library, allowing us to integrate MongoDB capabilities into our PHP application seamlessly. Once installed, we include Composer's autoloader in our script to ensure all necessary classes are available. We begin by creating an instance of the MongoDB client, where we specify the connection string, including the MongoDB server's user credentials and host details. This connection allows us to interact with the MongoDB server directly. After successfully connecting, we specify which database and collection we want to work with, in this case, the Productions database and the Movies collection. To retrieve data, we perform a query to find a specific movie by its title, 200 meters. The findOne method is utilized here, which retrieves a single document that meets the criteria. Finally, by using printer, we can output the retrieved movie's details, allowing us to verify that our query was successful and examine the data returned from the database. To connect with MongoDB using Ruby, the first step is to include the MongoDB gem in your gemfile, allowing you to utilize the driver in your application. After running the bundle install command, you can proceed to establish a connection with the MongoDB server. In this example, a client is created using the Mongo client class, specifying the server's address and the database name, Productions in this case. Once the client is set up, you can access the movies collection directly using the client instance. This streamlined approach allows you to perform database operations with ease. The code proceeds to query the collection for a movie document with the title 200 meters. By utilizing the find method, it retrieves the first matching document. Lastly, the result is printed to the console, showcasing Ruby's capability to handle MongoDB interactions efficiently. This concise code structure demonstrates Ruby's expressive syntax, making it an excellent choice for quick development, especially in web application contexts. Now that we've explored various programming languages and how they connect to MongoDB, let's briefly summarize the essential concepts we've covered. We started off by installing the necessary drivers or libraries for Node: JS, Python, PHP, and Ruby. Then, we wrote scripts to connect to the MongoDB server, opened a specific database, accessed a collection, and successfully queried data. To refine our understanding further, let's look at the broader strategies and potential challenges we might encounter when connecting to MongoDB. Depending on the application's configuration, you may need to consider details such as authentication mechanisms, network security, and data handling or migration strategies. And remember, while each programming language has its particular quirks and syntax, they all revolve around the core concept of interacting with a NoSQL database like MongoDB. Now that we've covered how to connect to MongoDB across different programming languages, the next crucial topic is performing CRUD operations. CRUD stands for Create, Read, Update, and Delete, operations fundamental to managing data effectively in any database. Stick around as we explore these operations in detail in our next session. The Using ODM stands out as a streamlined choice for connecting to MongoDB from your Ruby or Rails application. In this video, we will dive deep into Using, exploring its functionality, advantages, and how to effortlessly integrate it into your applications. So far, we learned about connecting to MongoDB using various programming languages, including Node, JS, Python, PHP, and Ruby. We covered the installation of necessary drivers, how to establish connections, access specific databases, and execute queries to retrieve data. Each language offers unique syntax and methods, but the core concepts remain consistent across all platforms. Next, we'll delve into using ODM libraries, specifically MongoDB, to simplify working with MongoDB in Ruby and Rails, and we'll explore CRUD operations within this framework. To begin incorporating MongoDB into your Rails application, you first need to specify the gem in your gemfile, allowing Bundler to manage its installation. Following that, you generate a configuration file, which is essential for establishing your database connection with MongoDB. The configuration file specifies crucial settings, including the database name and connection details, typically defaulting to a development environment setup. Once MongoDB is installed and configured, you can define your application's data models. In this example, we create a user model that inherits from MongoDB document. Here, we define 3 fields: name, email, and age, each assigned a specific data type. This setup mirrors the structure seen in Active Record, simplifying the transition for Rails developers. Moreover, we introduce validation rules directly within the model to ensure data integrity, specifically ensuring that the name must be present and that email addresses are unique. These validations act as a safeguard, preventing invalid data from being saved, thus enhancing the robustness of the application. Through this clear structure, MongoDB facilitates intuitive and powerful data management for Ruby on Rails applications. In this section, we will explore the basic create and read operations using MongoDB, focusing on how to manipulate user documents effectively. To create a new user, we begin by instantiating a user object with specific attributes, name, email, and age, and then we call the save method to store this document in the MongoDB database. Alternatively, we can leverage the convenient create method, which simplifies this process by combining instantiation and persistence in a single command. Moving on to the read operations, we can retrieve a user document by its unique ID using the find method, allowing us to access specific user data directly and efficiently. For more complex queries, such as finding all users over a certain age, we utilize the where method, which enables us to apply query conditions seamlessly. MongoDB also supports advanced querying, allowing us to chain conditions together, like finding users whose names start with a particular letter and meeting additional criteria, showcasing the flexibility and power of MongoDB in handling database interactions. To update a user's information in MongoDB, you typically start by retrieving the user document using their unique ID. This is done with the find method, allowing you to access the user's current attributes. Once you have the user object, you can modify its fields, such as name and age, by calling the update method with a hash of the changes you want to apply. This approach grants you full control over what gets updated while ensuring any validations defined in the user model are honored. Alternatively, if you want to update a user without loading the entire object into memory, MongoDB offers the update1 method. This is particularly useful in high-load applications where resource efficiency is critical. By specifying a condition, such as an email address, and using the set operator, you can directly update specific fields with minimal overhead. In scenarios where document deletion is necessary, MongoDB provides straightforward methods like destroy to remove a user by their ID, ensuring a clean removal process. For bulk deletions, delete all can be employed based on conditions, which skips validations and callbacks, streamlining the process for larger datasets. In this section, we'll look at how to establish relationships between documents in MongoDB. First, we define a user class that includes MongoDB document, which lets it function as a MongoDB model. Each user has a name field of type string, and importantly, we establish a has-many relationship with the posts collection. This means each user can have multiple associated posts. Similarly, the post class also inherits from MongoDB document and contains fields for title and content, representing the post's attributes. The belongs to declaration in the post class indicates that each post is linked to a single user, creating a direct relationship between the two models. When you create a user with userCreate, you can easily associate posts with that user by calling userPostsCreate. This creates a new post linked to the user, allowing for seamless retrieval and management of related documents. By leveraging these relationship functionalities, MongoDB simplifies interactions with your data, making your code cleaner and more intuitive. Now that we've set the foundation for our user model, let's take a closer look at how we enhance its functionality with indexing. In this example, we're introducing an index on the email field of the user model. The index is defined with a unique constraint, ensuring that no two users can register with the same email address. This is crucial for applications that require unique identifiers for users, such as login or account recovery processes. By declaring index, email, 1, unique, true, we instruct MongoDB to create an index that significantly speeds up query performance when searching for users by their email. The number 1 indicates ascending order for the index. Utilizing indexes accelerates data retrieval, particularly beneficial when working with large datasets, as it allows MongoDB to locate documents swiftly without scanning every record. However, it's essential to keep in mind that while indexes enhance read operations, they can introduce overhead during write operations, as MongoDB must update the index each time a document is added or modified. Therefore, careful consideration of which fields to index is necessary to optimize application performance effectively. To create a new migration in MongoDB, you begin by running a command that generates a migration file, specifically for adding new fields to existing models. In our example, we are adding an age field to the user's collection, which illustrates how you can adapt your database schema as your application evolves. This migration class includes two important methods, self-up and self-down. The self-up method is called when you apply the migration, where you can define changes like creating indexes to improve query performance. In this case, it invokes userCreateIndexes, which ensures that any necessary indexes are established to optimize data retrieval for future operations involving the user model. Conversely, self-down is there to handle the rollback process if you ever need to revert changes made by the migration. While in this instance the rollback logic is left blank, you could include any relevant steps to undo the updates. This systematic approach to schema management keeps your application organized and adaptable to changing data requirements. Thank you for joining me in this exploration of ODM libraries, specifically MongoDB. I hope this session has illuminated how to efficiently manage your MongoDB data using Ruby object-oriented techniques. If you have any questions or require further clarifications, don't hesitate to drop a comment below. Stay tuned for our upcoming lessons, where we'll dive even deeper into advanced MongoDB techniques and best practices. CRUD operations are fundamental to managing data in MongoDB, allowing you to create, read, update, and delete documents stored in the database. Whether you are building a web application, a data analysis tool, or just exploring the world of NoSQL databases, you'll find that mastering these operations is essential for effective database management. Today, we'll dive into what CRUD operations are, why they matter, and how to implement them effectively in MongoDB. So far, we learned about the advantages of using MongoDB as an object document mapper, ODM, in Ruby and Rails applications. We emphasized its ability to simplify interactions with MongoDB, discussed the installation process, configuration of MongoDB, defining models, and implementing validations. We outlined CRUD operations: create, read, update, and delete, including how to manage relationships between documents. Lastly, we touched on essential features such as indexing and migrations to enhance database performance and maintainability. Now, we will talk about the details of CRUD operations and see practical code examples for each. In this section, we will explore how to create documents in a MongoDB collection using specific operations. The insert1 method is used to insert a single document into the book's collection. In this example, we define the properties of the book, such as its title, ISBN, author, and price, structured in key-value pairs. When executed, the method not only adds the book to the collection, but also generates a unique identifier, id, for this document, allowing easy referencing in future operations. On the other hand, if you want to add multiple books simultaneously, the insert_many method is ideal. This method accepts an array of documents, enabling you to insert several records in one command. Here, we've outlined the titles, ISBNs, authors, and prices for 2 different books. The response from this method will inform you about the number of documents successfully inserted and provide their respective unique IDs. This capability is crucial for efficient data ingestion, especially when dealing with large amounts of information. Overall, both methods play a significant role in managing and organizing your data effectively. The read operation is essential for fetching data from your collections in MongoDB. To retrieve all documents in the book's collection, you can simply execute the find method without any parameters, which returns all records stored within that collection. However, most of the time, you'll be interested in finding specific documents. For example, if you want to locate a book by its ISBN, you would use find with a query object that specifies the ISBN. This approach allows you to filter results and return only the documents that meet your criteria. Furthermore, MongoDB's querying capabilities extend to utilizing logical operators like OR and AND. By using the OR operator, you can construct more complex queries, such as searching for all books written by either John Doe or Alice Johnson. This flexibility showcases MongoDB's powerful document-oriented nature, enabling you to perform intricate searches and efficiently manage your database records while giving you precise control over the data you retrieve. In this section, we will delve into the *update** operation, which is essential for modifying existing documents in MongoDB. The update1 method allows us to find a specific document matching a given filter and apply changes to it. For instance, when we want to update the price of the book with ISBN 101, we specify the filter criteria and use the set operator to assign a new price of $34.99. The method provides feedback indicating how many documents matched the query and were modified, helping confirm the operation's success. On the other hand, if you need to adjust multiple documents simultaneously, the update_many method comes into play. In our example, we seek to set a discount field to 10% for all books priced above 30. This method iteratively processes each document meeting the criteria, which is particularly advantageous for bulk updates or restructuring data efficiently. Understanding these operations is key to managing your datasets effectively and ensures that your database reflects changes in your application's requirements. In this section, we will explore the delete operation in MongoDB, which allows you to remove documents from your collections when they are no longer needed. To delete a single document, such as a book identified by its ISBN, we utilize the delete one method. By providing a filter that specifies the ISBN, the command effectively locates the document and removes it from the book's collection. This operation ensures that only the targeted document is affected, allowing for precise deletions. On the other hand, for situations where you need to eliminate multiple documents at once, such as removing all books that have a discount applied, we turn to the delete many method. By specifying a condition that targets documents with a discount field, this command will delete all relevant entries in one go. It's important to exercise caution with bulk deletions, as they cannot be undone once executed. Understanding how to correctly implement these methods empowers you to manage your data effectively and maintain the integrity of your collections. Wrapping things up, CRUD operations form the foundation of how we interact with MongoDB databases. We have covered how to create, read, update, and delete documents within a MongoDB collection using practical code examples. These operations empower you to efficiently manage your data and adapt to the needs of your applications seamlessly. As you continue on your journey with MongoDB, mastering these CRUD operations will not only enhance your ability to manage data, but also open up new possibilities for creating robust and dynamic applications. Remember, practice makes perfect, and the more you work with these CRUD methods, the more intuitive they will become. I hope this overview has provided valuable insights into CRUD operations in MongoDB. Keep experimenting with different scenarios, and don't hesitate to reach out if you have any questions or need further clarification on any topic discussed. Happy coding! In this video, we'll delve into advanced querying techniques in MongoDB that will help you harness its full potential and optimize your database queries. Understanding these techniques will significantly improve your application's performance by allowing you to efficiently retrieve the data you need. So far, we learned about CRUD operations in MongoDB, which include creating, reading, updating, and deleting documents. We explored practical implementations with code examples for each operation, illustrating how to effectively manage data within a MongoDB collection. Additionally, we discussed the importance of these operations in building robust applications and how they contribute to efficient database management. As we progress, we will cover advanced querying strategies, indexing, and aggregation frameworks to enhance our querying efficiency. In this section, we delve into how to efficiently filter documents in MongoDB using comparison operators. The provided command retrieves all documents from the products collection where the price exceeds $50. The use of the GT operator illustrates the ability to specify conditions that find data based on numerical comparisons, enhancing your query capabilities. This flexibility allows you to tailor your search results based on specific criteria, such as price, ratings, or any other numeric attributes in your database. By leveraging comparison operators, you can create more precise queries that help you hone in on the exact data you need, improving the overall efficiency of data retrieval. Understanding and utilizing these operators allows you to better manage your dataset, ensuring your application serves user needs more effectively. This is just the beginning of how you can refine your queries in MongoDB, leading to more advanced querying possibilities as we progress. In this section, we will explore how to use the OR operator in MongoDB to create queries that match multiple criteria. The query syntax begins with DB products, find, which indicates that we are searching the products collection for specific documents. Within the parentheses, we specify the conditions using the OR operator, which allows us to combine multiple criteria into a single query. In this case, we are looking for products that either have a color of red or a price that is less than $30. This is defined using an array structure containing two conditions, one for the color and another for the price. The color, red, condition checks whether the product's color matches, while price, LT30, applies a comparison operator to find products priced below $30. By utilizing the OR operator, we enhance our querying capability, enabling us to retrieve a diverse set of documents that meet at least one of the specified criteria. This approach provides greater flexibility in managing data retrieval and allows for more granular search results based on varied customer needs. When working with collections that have array fields, MongoDB provides powerful array operators to streamline your queries. For instance, if you want to find orders that specifically include a product, such as a laptop, you can simply query the items array in the orders collection. This query scans the items array for any occurrence of the specified product and retrieves all matching documents. Similarly, if your requirement is to filter orders based on the number of items they contain, you can leverage the size operator. By specifying the size of the items array you are interested in, let's say exactly 3 items, MongoDB will return only those documents that match this criterion. Using these array operators not only simplifies the querying process, but also enhances the efficiency of retrieving nested data structures, allowing for more refined control over your data retrieval efforts. To calculate the total sales from the sales collection using the aggregation framework, we utilize the aggregate method, which is designed for processing data and returning computed results. The heart of this operation is the group stage, which consolidates documents based on specified fields, but here we set id to null. This means we are not grouping by any specific identifier. Instead, we're aggregating all documents as a single group. Within this group, we employ the sum operator to compute the total of the amount field across all documents in the collection. This operation provides a straightforward and efficient way to generate a summary value, reflecting the collective sales information. Understanding this structure is vital, as it highlights how powerful the aggregation framework can be for performing complex calculations and generating insights from your data efficiently. To enhance the performance of your queries in MongoDB, indexing plays a pivotal role. The command to create an index on the price field in the products collection uses the createIndex method with a specified field and direction. In this case, by setting the price to 1, you're creating an ascending index. This index significantly speeds up the data retrieval processes for queries that filter or sort documents based on the price. While indexes bring substantial benefits for read operations, it's essential to note that they can introduce overhead during write operations. Each time a document is added, modified, or deleted, the index must be updated, potentially impacting performance if not managed wisely. Therefore, it is crucial to assess your application's read versus write patterns when determining which fields to index. Understanding these nuances will help you leverage indexing effectively, balancing performance improvements with the overhead associated with maintaining those indexes. In this section, we will explore the use of the facet stage in MongoDB's aggregation framework, which allows for executing multiple aggregation pipelines simultaneously within a single query. This approach is highly efficient, as it enables us to retrieve different types of aggregated results at once without making multiple calls to the database. The provided code utilizes the facet operator to create 2 distinct aggregation pipelines, one for calculating the average price of products and another for counting the total number of products in the collection. Within the first pipeline, a group stage is employed to compute the average price. It does so by grouping all documents together, id, null, and applying the AVG operator to the price field. Meanwhile, the second pipeline simply counts all documents using the count operator with a specified output field named count. By leveraging the facet stage, we optimize data retrieval, allowing us to gain comprehensive insights into a collection's average price and total product count in a single aggregated query. This method enhances performance considerably when analyzing large data sets. To enable full-text search capabilities in your MongoDB application, you first need to create a text index on the fields that contain the text you want to search. In our case, we create a text index on the description field of the products collection. This index enhances the search performance by allowing MongoDB to efficiently locate documents based on textual content. Once the text index is established, you can leverage the power of the text operator. This operator enables you to perform search queries that match specific keywords within the indexed fields. For instance, searching for the term gaming in the description will return all documents that contain this keyword, making it easier for users to find relevant products effortlessly. The combination of creating a text index and using the text operator is especially powerful in applications where users need to execute searches for specific terms within large volumes of text data, significantly improving user experience and functionality. In this segment, we will focus on the importance of the explain method in MongoDB for analyzing query performance. The command db products find price lt50 explain execution stats is a powerful tool that gives you comprehensive insights into how your query operates under the hood. When you execute this command, MongoDB provides detailed execution statistics about your query, including information on the number of documents examined, the number of documents returned, and whether any indexes were utilized during the query process. This level of detail is crucial for identifying potential bottlenecks or inefficiencies in your queries. By examining these metrics, you can determine if your existing indexing strategies are effective or if further optimization is necessary. Moreover, understanding the execution path of your queries allows you to refine your database interactions, ultimately leading to enhanced performance. By leveraging the insights gained from the explain plan, you can make informed decisions about indexing, query construction, and overall data management, ensuring that your application runs smoothly and efficiently. In conclusion, advanced querying techniques in MongoDB empower you to tap into the full potential of your data store. By mastering query operators, logical operations, aggregation frameworks, indexing, text search, and explain plans, you're setting yourself up for success in building high-performance applications. These techniques provide more refined control and efficiency in how you manage and retrieve data, paving the way for robust application development. As MongoDB evolves, continuous learning and experimentation are key to leveraging these capabilities fully. Happy querying! In the dynamic world of database management, the decisions you make about structuring and representing data significantly impact efficiency, adaptability, and overall system performance. Today, we are diving into an introductory lesson on MongoDB schema design, a crucial aspect that influences how data is organized and accessed in applications. So far, we have explored advanced querying techniques in MongoDB, focusing on optimizing database performance through precise operations. Now, let's shift gears and talk about the significance of schema design, its principles, and how it shapes our data management strategies. In this example, we delve into a user document structure in MongoDB that showcases how data is organized within a single document. The document begins with a unique identifier, represented by the id field, which uses Objected to ensure each record remains distinct. Following this, the useId field captures the name of the user, while the age field provides a straightforward integer representation of the user's age. One noteworthy feature of this schema is the embedded document for the user's address, encapsulated within the address field. This allows for an efficient grouping of related data, such as country, city, and street, streamlining data access without involving joins, which is typical in relational databases. The inclusion of an array named hobbies also highlights MongoDB's flexible document model, supporting varied data types directly within the structure. This organization allows for rapid retrieval of all related user data in a single query, underscoring the benefits of MongoDB's schema design for application-specific requirements. Overall, this document structure exemplifies the principles of embedded data for enhanced performance and simplicity in access patterns. In this example, we can see a document representation of a blog post in MongoDB, demonstrating how to embed related comments directly within the post itself. The document starts with a unique identifier, id, which is crucial for MongoDB's internal process of distinguishing between different records. The field's title and body contain the content of the blog post, providing context for the embedded comments. The comments field is an array, showcasing a list of comment objects associated with the post. Each comment object includes essential information, such as the user who made the comment text itself, and the date the comment was made. This structure exemplifies the embedding principle, enabling you to fetch all relevant data in a single query. By organizing related data this way, performance is enhanced, particularly in scenarios where the posts and their comments are accessed frequently. However, it's crucial to monitor the size of the document, as a large number of embedded comments could necessitate a re-evaluation towards a referencing system for better management. Thus, understanding these design choices is vital in shaping efficient database applications. In this example, we illustrate how to structure posts and comments in MongoDB using a referencing approach, which is especially effective in scenarios where data relationships require flexibility. The post collection holds information for each blog post, including the unique identifier, title, and content body. Instead of embedding comments directly within the post, we reference them through their unique identifiers, allowing comments to reside in their own separate comment collection. This separation not only maintains a normalized schema, but also facilitates easier management of comments, which can rapidly increase in number as user engagement grows. Each comment document contains its own unique identifier, the username of the commenter, the comment text, and a timestamp, effectively linking it back to the relevant post. This design allows for independent manipulation of comments, such as adding or deleting without altering the entire post document. By referencing comments, we are able to optimize read operations while maintaining the ability to scale, ensuring organized data management as interactions with the posts evolve. This approach strikes a balance between performance and adaptability to changing data patterns in our web application. In this section, we explore an important example of a BSON document structure in MongoDB. The document begins with a unique identifier, id, which is automatically generated using the objected function. This ensures that every document is distinct within the database, allowing for efficient indexing and retrieval. Next, we encounter a variety of fields demonstrating BSON's flexibility. The string field, which contains a simple string, showcases how textual data can be stored directly in the document. The array field illustrates BSON's capability to handle arrays, accommodating a list of integers for versatile data manipulation. Additionally, the object field exemplifies the ability to nest documents, allowing for complex data relationships by encapsulating the name and age properties within another document structure. This enhances data organization, making it easier to retrieve related information without complicated queries. Moreover, the inclusion of a Boolean field demonstrates how MongoDB can store true-false values, while the date field highlights the support for precise date and time representations using ISODate. Overall, this document structure showcases BSON's strengths in managing diverse data types efficiently, making it an indispensable format for modern applications. In conclusion, effective MongoDB schema design takes thoughtful consideration of data access patterns, efficient embedding, and referencing strategies that align with your application's performance requirements. As we move forward, it's essential to apply these principles in practice and explore real-world examples of how they manifest within databases. So far, we've learned about the architecture of schema design in MongoDB. Now, we will dive deeper into specific design patterns and best practices that can help enhance the performance and scalability of your applications. Whether through embedding, referencing, or effective use of BSON, mastering these concepts will support you in optimizing your MongoDB experience. Remember, the schema you create today should be adaptable for the complexities of tomorrow. Happy coding! In today's lesson, we're diving into advanced data modeling techniques in MongoDB, exploring design patterns that enable tailored schema designs for optimal performance and scalability. We'll build upon our prior discussions regarding schema design fundamentals, the embedding and referencing strategies, and the flexibility BSON provides. So far, we learned about the critical aspects of MongoDB schema design, emphasizing the importance of structuring data for efficiency and performance. We discussed the differences between embedding and referencing data based on access and modification needs, and highlighted the role of BSON in enhancing document flexibility. Additionally, we explored how understanding your application's read-write ratio can guide effective design strategies. As we proceed, we'll delve into specific design patterns and best practices to further optimize your MongoDB applications. In this section, we will explore a practical implementation of the singleton pattern in MongoDB, which is ideal for managing application settings stored in a single document. The first part of our code example demonstrates how we can create a configuration document within a MongoDB collection called Settings. By structuring all relevant settings into one document, we define attributes such as the application name, version, and features, ensuring that retrieval and updates are straightforward and efficient. This setup minimizes lookup times and avoids potential duplicates that could arise from multiple documents. The second part of the code illustrates how to fetch this configuration document using a single line of code. By employing the find_one method, we can easily retrieve the settings based on its unique identifier id. This efficient querying mechanism allows our application to access configuration data quickly, which is crucial for maintaining high performance. Leveraging the singleton pattern not only simplifies the schema design, but also enhances the overall efficiency of data retrieval within our application. In our aggregation query, we utilize MongoDB's powerful aggregation framework to summarize sales data by product category. The code showcases the use of the aggregate method on the sales collection, which is designed to perform complex data manipulations directly within the database. Within the aggregation pipeline, we apply the group stage to group documents by the category field. This grouping is essential for organizing the data in a way that enables us to compute totals specific to each category. The use of the total sales field alongside the sum operator allows us to calculate the total amount of sales within each group, efficiently aggregating data without needing to process it in the application layer. Finally, the results are converted into an array using the toArray method, yielding a structured output of categories with their corresponding total sales figures. This method of processing not only keeps network load to a minimum, since we retrieve just the computed results, but also enhances performance by leveraging MongoDB's built-in capabilities for data aggregation. Thus, this aggregation approach is invaluable for generating insights effectively. In the polymorphic associations pattern, we streamline how comments are related to various entities, such as products or posts, within a single comments collection. The first piece of code showcases a JSON representation of a comment document, which includes a unique identifier id, the content of the comment, the entity id referencing the associated product, and the entity type indicating the nature of that relationship. This structure eliminates the need for multiple collections for different entity types, thus promoting efficiency and clarity in your database design. The second code snippet illustrates how to retrieve comments specific to a product. By issuing a query that filters the comments based on entity type as product, and matching the entity id with the given product id, you can efficiently fetch all relevant comments. This method not only optimizes data retrieval, but also keeps your schema organized and versatile, crucial for maintaining performance in applications where the nature of associations can vary widely. Overall, this approach underscores the flexibility and efficiency that polymorphic associations bring to managing relationships between different data entities in MongoDB. In the context of sharding in MongoDB, the provided code demonstrates how to structure user documents and set up sharding for a collection. The first part of the code represents a MongoDB document for a user which includes fields such as ID, USID, name, and email. This structure is essential as it encapsulates user information that will be distributed across different shards in the database. Using a unique shard key, like USID, helps ensure balanced data distribution across the shards, improving performance and scalability as the user base grows. The second part of the code is a MongoDB shell command that initializes the sharding process for the user's collection within the MyDatabase database. By invoking the shard collection function alongside the shard key specification for USID, you enable the database to distribute documents in this collection based on the value of USID. This setup is crucial for handling high volumes of traffic and large datasets efficiently, allowing for quick access and management of user data through targeted queries in a sharded environment. In the context of the event sourcing pattern, understanding how your application can effectively manage and record events is crucial. The first code snippet represents an event document that logs a deposit transaction in a banking application. Each field in this document serves a specific purpose. The ID uniquely identifies the event, while accounted associates this transaction with a specific account. The event type indicates the nature of the transaction, here labeled as a deposit, and the amount reflects the value of the transaction. Lastly, the timestamp provides a precise record of when the event occurred, which is key for maintaining an accurate history of account activities. The subsequent code snippet focuses on how to aggregate and retrieve the total deposits and withdrawals for an account. It uses MongoDB's aggregation framework to efficiently compute the sums of the respective types of transactions. The match stage filters events specific to the accounted and event type, while the group stage calculates the total amounts accordingly. This operation not only emphasizes the power of MongoDB in handling complex queries, but also showcases how event-driven systems can seamlessly reconstruct state and facilitate comprehensive reporting on account activities. In the context of implementing the CQRS pattern, this code snippet represents a sample write model used for managing user data in a MongoDB collection. Here, the document structure is tailored for efficient writes, showcasing a denormalized format. The document begins with a unique identifier, ID, which utilizes MongoDB's object-ID to ensure that each user profile is distinctly recognizable within the database. The USID field captures the unique identifier for each user, essential for linking user interactions to their profiles. The Preferences object encapsulates user settings, such as the chosen theme and notification preferences, allowing for easy retrieval and updates of user-specific configurations. By structuring the data this way, we prioritize write efficiency over read optimization. This is particularly useful in scenarios where users frequently update their preferences, as the design minimizes the complexity of document modifications. With the CQRS pattern, this write model can coexist with a separate read model that might optimize data retrieval processes, demonstrating the power of separating read and write operations to enhance scalability and performance within the application. In conclusion, advanced data modeling techniques in MongoDB allow for tailored schema designs that promote performance and scalability, a must in today's data-driven applications. By mastering design patterns such as singleton, aggregation, polymorphic associations, sharding, event sourcing, and CQRS, you equip yourself with the tools to create robust and efficient data management systems. Keeping your schemas flexible and your operations efficient is essential for a thriving application. As we move forward, applying these patterns in practical scenarios can significantly enhance your MongoDB experience. Make sure to experiment with these techniques in your projects, as hands-on practice will solidify your understanding and improve your data modeling skills. Happy coding! The aggregation framework in MongoDB is a powerful data processing tool that allows you to perform complex data transformations and computations with ease. It provides a comprehensive way to work with data directly within the database, streamlining the manipulation and analysis processes. In this video, we'll take an in-depth look at the aggregation framework, exploring how it can simplify complex data operations and enhance your data analysis capabilities. So far, we covered advanced data modeling techniques in MongoDB, emphasizing effective schema design for better performance and scalability. We delved into various design patterns, sharding, event sourcing, and the CQRS pattern, setting the foundation for robust application performance. Now, we will dive into the aggregation framework, exploring its stages, operators, and practical examples to better understand how to leverage it for data transformation and analysis. In this section, we delve into how to utilize MongoDB's aggregation framework to calculate the average grade per student for a specified semester. The first step in our pipeline employs the match stage to filter documents, ensuring we are only working with grades from the fall 2023 semester. This is crucial as it limits the dataset, enhancing efficiency by allowing subsequent stages to operate on less data. Following the filtering, the group stage consolidates the grades by studented. Here, we calculate total grade using sum, which aggregates the grades for each student, while also counting the number of courses taken with total courses through the count operator. This prepares us for calculating averages in the next step. Finally, we reach the project stage, where we compute the average grade. This is done by dividing total grade by total courses, effectively yielding the average grade for each student. The result of this aggregation pipeline provides valuable insights, allowing the university to assess student performance efficiently and accurately. Overall, this approach effectively showcases the power and flexibility of the aggregation framework in handling complex data analysis tasks. In this segment, we'll explore a practical example using the match stage of the aggregation framework. This code snippet illustrates how to filter documents based on specific criteria, in this case, retrieving users older than 22 years. The match stage is essential for narrowing down your dataset before proceeding with further processing. By applying this filter at the beginning of your aggregation pipeline, you enhance performance, as MongoDB only needs to process a smaller subset of documents. This efficiency is particularly beneficial in large datasets where processing time can significantly impact application performance. Here, you see the command querying the user's collection, explicitly stating the condition for filtering. Age must be greater than 22. This operation leads to a straightforward yet powerful result. Only the relevant documents that satisfy this condition are passed to the subsequent stages of the pipeline, allowing for streamlined data manipulation. Ultimately, using match not only helps you maintain a clean pipeline, but also ensures that follow-up stages operate on a manageable set of data, which enhances overall execution speed. The aggregation framework provides several powerful stages to manipulate and analyze your data effectively. One such stage is the group stage, which is essential for aggregating data based on a specified key. In the example provided, we group users by their country, allowing us to calculate the average age of users within each country. This not only simplifies data insights, but also helps identify demographic trends effectively. Another critical stage is unwind, which serves the purpose of flattening array fields within documents. For instance, if each user has an array of hobbies, applying unwind on the hobbies field transforms the data structure, creating separate documents for each hobby. This process enhances data clarity and facilitates more straightforward analysis, as each hobby can now be treated as an individual document rather than being nested within the user document. Ultimately, these stages illustrate how the aggregation framework enables more intuitive and efficient data analysis. In this code snippet, we utilize the lookup stage within the aggregation framework of MongoDB to combine documents from two separate collections, specifically orders and products. This stage is essential as it allows us to perform operations akin to SQL joins, thereby enriching our data analysis. Here, we specify that we want to join the orders collection with the products collection. The local field parameter indicates the field in the orders collection that contains the product identifier, which is producted. Simultaneously, the foreign field parameter represents the field in the products collection that we will match against, which is the id field. The results of this join will be stored in a new array field named product details within each ODA document. This structure allows each ODA to be more informative by integrating associated product details, enabling deeper insights into sales and inventory management. As a result, the output not only presents the ODA data, but also enriches it with critical product information, facilitating comprehensive analyses for better decision-making. In this part of the aggregation pipeline, we utilize the project stage to reshape our documents efficiently. The project operator enables us to control which fields are included in the output documents by explicitly defining them. In this example, we focus on returning only the username and phone number fields from the user documents while excluding all other fields. This approach is particularly useful when we want to narrow down the output to essential information, improving the performance of our queries by reducing the data being processed and transmitted. By specifying the fields we want, we also enhance the clarity of the results, making it easier to extract meaningful insights without the distraction of extraneous data. Furthermore, using the project stage allows for potential data transformation. We could also introduce calculated fields or manipulate existing ones as necessary. Overall, project serves as a powerful tool in the aggregation framework, giving us fine-grained control over the structure and content of our output documents, streamlining data analysis and making it more efficient. To summarize, the MongoDB aggregation framework is simply a robust tool incorporating a variety of stages for data transformation and analysis. The blend of performance, flexibility, data integrity, and resource efficiency allows developers and data analysts to orchestrate sophisticated data workflows. At this point, you should now have a foundational understanding of what the aggregation framework is and how it operates through various stages. With this knowledge, you can start building powerful pipelines to manipulate and analyze your data programmatically, leveraging the full capabilities of MongoDB in your applications. So take these tools and go forth, transforming your data like a pro. In our next lesson, we will explore advanced querying techniques in MongoDB that build on the aggregation framework, opening up even more possibilities for data management and insight generation. Stay tuned. In this lesson, we will be diving into the world of advanced querying techniques in MongoDB, unlocking new capabilities in data management and retrieval. So far, we have explored the MongoDB aggregation framework, a powerful tool that enables complex data transformations and computations directly within the database. We covered the structure of the data processing pipeline, including stages like match, group, and project, which empower us to filter, group, and reshape data efficiently. Next, we will dive deeper into advanced querying techniques that can take our data management and query optimization skills to the next level. In this section, we will explore how to create indexes in a MongoDB collection, which is essential for optimizing query performance. The first command demonstrates how to create a single-field index on the username field of the user's collection. By specifying username 1, we are instructing MongoDB to create an ascending index, which significantly speeds up queries that filter or sort based on usernames. This is particularly beneficial when dealing with large datasets, where scanning every document would be inefficient. Next, we illustrate the creation of a compound index with the command that indexes both the first name and last name fields. By combining fields in an index, MongoDB can perform more comprehensive queries efficiently, enhancing search capabilities across multiple attributes simultaneously. However, it's important to understand that while indexes improve read operations, they can introduce overhead during write operations, as the index must be updated with each insert, update, or delete. Hence, careful consideration is necessary when designing indexes to balance read performance and maintenance costs. To enable efficient text search capabilities in MongoDB, you first need to create a text index on the relevant field in your collection. By executing the command to create a text index on the content field of the posts collection, you are instructing MongoDB to optimize searches for words and phrases within that field. This index allows you to leverage MongoDB's built-in full-text search features, dramatically improving the speed and efficiency of search queries. Once the text index is established, you can utilize the text operator to perform searches within the indexed field. For instance, when you search for the term MongoDB, the command executes a query that not only retrieves documents containing that exact term, but also understands variations and related terms through linguistic processing. This powerful feature caters to natural language queries, making your search functionality robust and user-friendly. Furthermore, you can enhance your search results by combining terms using logical operators, such as searching for documents that mention both MongoDB and database. This capability allows for more precise filtering of results, enabling users to find exactly what they are looking for amidst a wealth of content. In this section, we will explore the facet stage of the aggregation framework, which allows us to perform multiple independent aggregations within a single query. The code snippet demonstrates how to analyze a collection of orders to gather insights about total sales and the number of orders made in a specified timeframe. The query initiates by using the DB orders aggregate method, targeting the orders collection. Inside the aggregation pipeline, the facet stage is introduced, which defines two independent pipelines, one for calculating total sales and another for counting the total orders. In the first pipeline, we apply the match stage to filter orders based on the order date, ensuring we only consider those from the beginning of the year 2023 onward, followed by the group stage to aggregate the results, summing up the amount field to retrieve the total sales. Meanwhile, the second pipeline also starts with a match to filter for the same date range, but instead of grouping, it uses the count stage to tally the total number of orders placed. This efficient use of the facet feature enables us to fetch rich analytics seamlessly, reducing the number of queries sent to the database. In this section, we are utilizing the lookup stage of the MongoDB aggregation framework to perform join-like operations between two collections, orders and customers. This stage is invaluable when you want to enrich documents from one collection with related data from another. Here, we are aggregating documents from the orders collection. The lookup operator takes an object that specifies the parameters for the join operation. The from field indicates the name of the collection we want to join with, which in this case is customers. The local field parameter specifies the field in the orders collection that will match a field in the customers collection. We are using customed for this purpose. The foreign field is the corresponding field in the customers collection, identified by id. Finally, the results of this lookup will be stored in a new array field called customer details. This enables us to access customer information directly alongside each order, facilitating a more interconnected data representation and enhancing our query results with relevant customer insights. In this section, we will focus on implementing geospatial queries to find locations based on geographical coordinates. First, you need to create a 2D index on the location field of the stars collection. This index, represented by 2D sphere, enables MongoDB to process geospatial data effectively, allowing for accurate calculations of distance between points. Once the index is created, you can perform a query to find all stars within a specified radius of a given point. The near operator is used here, which specifies that the search should be near the location defined by a point geometry, indicated by the longitude and latitude coordinates. Additionally, you can limit the results to a maximum distance, such as 5,000 meters, which allows users to look for nearby stars efficiently. This capability to access and analyze geospatial data is invaluable for applications focusing on location-based services, enabling businesses to tailor their offerings based on proximity and enhance user experience by guiding them to the nearest locations or assessing market dynamics effectively. In scenarios where you need to query documents containing specific elements within an array, the match operator becomes invaluable. In the provided query, we are targeting the products collection to find documents where the reviews array contains at least one review that has a rating of 5 stars. This is essential for effectively filtering complex data structures that include nested arrays. By wrapping the criteria within LM-Match, we ensure that MongoDB evaluates the conditions specifically for the elements within the reviews array, allowing it to return only those products that meet the specified requirement. This level of querying not only simplifies the search process, but also enhances performance as it limits the results to documents that have relevant content. Such sophisticated querying capabilities allow developers to gain actionable insights from their datasets, especially when dealing with user feedback or product evaluations within applications. Overall, using LM-Match opens up new possibilities for analyzing data and understanding user sentiment, making it a powerful feature in the MongoDB querying arsenal. In this snippet, we focus on implementing pagination for efficient data retrieval. The code initializes a variable named page, set to 2, which indicates that the user wishes to access the second page of results. Simultaneously, page size is defined as 10, indicating the desired number of products to display on each page. The pagination is executed through the MongoDB query by using the skip and limit methods. The skip function is calculated by taking the current page number -1 and multiplying it by the page size. This effectively skips the earlier products on previous pages and starts at the appropriate point in the dataset. In our case, it skips the first 10 products, allowing the user to see the next set of 10. Lastly, the limit method confines the results returned to just those 10 products. This structured approach to pagination ensures users are not overwhelmed by large datasets and can navigate data seamlessly, thus enhancing the overall user experience. In this part of the lesson, we will focus on implementing role-based access control to enhance data security in our MongoDB database. The code provided creates a new user with specific permissions. Here, we're defining a user named read-only user with a password set to password 123. This user is granted a role of read, specifically for a collection called products within the database referred to as your database. This means that the read-only user will have permission only to read data from the products collection and will be restricted from performing any other operations, such as inserting or deleting documents. By implementing such user roles, you can effectively manage data access, ensuring only authorized users can view or manipulate specific information. This approach mitigates the risk of unauthorized access to sensitive data while promoting a structured method for user permissions in your application, aligning perfectly with best practices for database security. Overall, advanced querying techniques in MongoDB not only enhance the efficiency and effectiveness of data interaction, but also allow developers to build increasingly sophisticated applications. From indexing to text search, geospatial queries to aggregation stages, the tools available to us represent a robust framework for data management. By mastering these techniques, you can significantly elevate the capability of your applications, creating user experiences that are not just functional, but also engaging and insightful. So, as we wrap up this lesson, remember that ongoing practice and experimentation with these concepts are key to gaining proficiency in MongoDB. In our next session, we will focus on optimizing queries for performance and exploring additional tools for managing data efficiently. Stay tuned for more exciting content and deepen your understanding of MongoDB. Aggregations in MongoDB are operations consisting of several steps that process multiple documents and return computed results. They are a powerful way to manipulate and analyze your data, allowing us to perform complex operations, such as filtering, grouping, and reshaping data. So far, we learned about advanced querying techniques in MongoDB, including the aggregation framework and indexing to enhance data management and retrieval. We explored creating indexes for performance improvements, utilizing text search for efficient string searches, and employing the lookup stage for combining documents from different collections. Additionally, we covered geospatial queries for location-based services, using LM-Match for querying array elements and implementing pagination for better data access. Lastly, we discussed the importance of security through role-based access control to protect sensitive information in our databases. Now, we will talk about the intricacies of the aggregation framework in MongoDB and how you can leverage its capabilities to derive meaningful insights from your data. In this code, we utilize the match stage of the MongoDB aggregation framework to filter documents based on a specified criteria, specifically targeting products with a price greater than $100. The match stage acts similarly to the find method, but is significantly more powerful within an aggregation pipeline, enabling us to narrow down the dataset effectively at the beginning of our process. By establishing this preliminary filter, we ensure that only relevant documents proceed to the subsequent stages of the pipeline, which not only improves efficiency, but also simplifies the data we will work with later on. Here, we specify our condition using the GT operator, which checks if the price field in our documents exceeds the value of 100. As a result, this aggregation query outputs documents that meet this requirement, allowing us to focus on more expensive products. This early filtering step is crucial because it sets the foundation for any further aggregation operations, such as grouping or sorting, thus helping us derive meaningful insights from a more manageable subset of data. In this code snippet, we utilize the group stage of the MongoDB aggregation framework to summarize sales data by product category. The ID field is set to category, which instructs MongoDB to group the documents based on the values found in the category field. This is crucial for analyzing data at a categorical level, allowing us to understand how different product categories contribute to overall sales. We also introduce the total sales field, which employs the sum operator to calculate the total of the amount field for each group of documents. This aggregated total provides insights into the sales performance of each category, enabling business decisions based on this analysis. When executed, the output will show a list where each category is associated with its respective total sales, facilitating a clear comparison and evaluation of sales across categories. This powerful feature of grouping, combined with aggregation functions, lays the groundwork for more complex analyses in subsequent stages. In this section, we introduce the sort stage of the MongoDB aggregation framework, which is essential for organizing output data meaningfully. After performing the grouping operation that totals sales by category, we want to enhance our results by sorting them based on the total sales amount. The inclusion of the sort stage right after the group stage is crucial. It enables us to arrange the output in descending order of the total sales field. By specifying sort total sales, the aggregation pipeline effectively places the categories with the highest sales at the top of the results. This sorting mechanism streamlines data analysis by allowing us to quickly identify which product categories are performing the best in terms of sales. Such an approach not only enhances clarity in data presentation, but also facilitates better decision-making based on these insights. Thus, integrating sorting following a grouping operation is a powerful way to derive actionable information from your aggregated data. In this section, we will explore the use of the project stage in the MongoDB aggregation pipeline to reshape our output after performing calculations. After grouping the sales data by category and computing the total sales for each category, the next step is to refine the output format. The project stage serves a crucial role by allowing us to select which fields to include or exclude in the final output. Specifically, this code snippet renames the grouped ID field to category, presenting it in a more user-friendly manner while also including the total sales. Importantly, we set ID to 0 to exclude the default MongoDB identifier from the results. This step is particularly beneficial when preparing data for analysis or presentation, ensuring that the output is concise and relevant to stakeholders. By focusing only on the essential information, category, and total sales, we streamline our data visualization or reporting processes, making insights easier to derive. Overall, the use of the project stage enhances data readability and utility. In this example, we utilize the aggregation framework to analyze sales data for the year 2023. The pipeline begins with a match stage that filters the records to include only those sales that occurred within the specified date range, from January 1, 2023 to December 31, 2023. This is crucial for narrowing down the data set, allowing for more efficient processing in subsequent stages. After the filtering, we implement the group stage, which categorizes the sales by product category and computes the total sales amount for each category using the sum operator. This step helps in summarizing the data effectively, providing insights into how each category performed over the specified time frame. Next, we apply the sort stage to arrange the results in descending order based on total sales, enabling easy identification of the top-performing categories. Finally, the project stage reshapes the output, renaming the grouped field ID to category, including the total sales, and excluding the default ID field. This streamlined output makes it simpler for analysis and reporting, showcasing the efficiency of combining multiple aggregation stages in a single query. In this section, we will explore how the lookup operator enables us to join data from different collections, thereby enriching our information for more insightful analysis. The code begins by initiating an aggregation on the orders collection using lookup, which allows us to bring in related data from the customer's collection. Specifically, it matches each order's customer ID with the corresponding ID in the customer's collection, creating an array called customer info that contains the relevant customer details. Next, the unwind stage is employed to flatten this array, so we can individually analyze each customer's information rather than dealing with nested data. This flattening prepares the data for the subsequent grouping stage. Here, the group operator aggregates the results based on the customer's name, summarizing the total amount spent by each customer. The use of sum amount within the grouping process allows us to efficiently calculate cumulative spending for each customer, transforming scattered order data into meaningful, actionable insights. This demonstrates the power of the aggregation framework in deriving complex relationships across collections, ultimately enhancing our data analysis capabilities. In this example, we utilize the facet operator within the MongoDB aggregation framework to run multiple aggregation pipelines at once. The operator provides a powerful way to execute complex queries that derive various insights simultaneously without making multiple database calls. Here, we have defined two separate aggregation pipelines. The first pipeline calculates the total sales across all records by grouping the documents and summing the amount field, presenting a comprehensive overview of sales performance in a single output. The second pipeline categorizes the sales data by the category field, providing a breakdown of total sales for each category. This is achieved through another grouping stage that also sums the amount field for each category. By incorporating a sorting stage, we ensure that the results are ordered by total sales in descending order, allowing for quick identification of the highest performing categories. This dual output format greatly enhances reporting capabilities, making it easier to analyze overall sales alongside segmented data. Thus, the facet operator serves as an excellent solution for aggregating multiple perspectives of data in one efficient query. To optimize query performance in MongoDB, creating indexes is a crucial step, especially for fields that are frequently used in aggregate queries. In the code provided, we create an index on the date field of the sales collection. This action enhances the efficiency of our aggregation operations when we filter, group, or sort data based on the date. By having an index in place, MongoDB can quickly locate the relevant documents, significantly reducing the time taken to execute those queries. Indexing plays a vital role in managing large datasets where aggregation may involve multiple stages. With an index on the date field, our aggregation queries can run faster, enabling a more responsive application. This practice not only improves query execution times, but also contributes to better resource management on the database server. Implementing such optimization techniques is essential for developers looking to enhance their application's performance and provide seamless user experiences, particularly when analyzing extensive data sets using the aggregation framework. In conclusion, the aggregation framework in MongoDB is an incredibly versatile tool that fulfills a broad range of data manipulation and analysis needs. By mastering its various stages, such as match, group, sort, project, and beyond, you can efficiently extract valuable insights and enhance data management in your applications. So far, we covered how to construct aggregation pipelines, apply filters, group data, sort results, and even combine information from multiple collections. Now, as you move forward, continue exploring these concepts in depth and applying them to real-world scenarios to fully leverage the power of data that MongoDB offers. Keep practicing with different aggregation queries, and soon you'll find yourself mastering the art of data analysis in MongoDB. In this video, we're diving into advanced aggregation techniques in MongoDB, a powerful tool for data analysis that can transform the way you handle your datasets. You'll learn about new operators and features that enhance your ability to process data effectively. So far, we learned about the aggregation framework in MongoDB, viewing it as a data processing pipeline with stages like match, group, and sort. We explored how to filter, group, and reshape data to derive meaningful insights, including the use of lookup for joining collections and facet for executing multiple pipelines. Additionally, we discussed performance optimization techniques, such as creating indexes for efficient data processing. Now, we will delve deeper into these concepts and their practical applications in data analysis. In this segment, we'll focus on the aggregation process using the add fields operator, which facilitates the addition of new fields to documents within your pipeline. Here, we start with documents representing products in a collection, each containing an ID, name, price, and tax rate. The goal is to calculate the final price of each product, inclusive of tax. To achieve this, we employ the add fields stage in our aggregation pipeline. We introduce a new field called final price, which is computed by multiplying the price by the sum of 1 and the tax rate. This multiplication ensures that the tax amount is effectively added to the original price, providing the customer with the total cost at checkout. This operation showcases the flexibility of the aggregation framework, enabling you to derive valuable insights directly within the data processing flow without needing to modify the original documents. By incorporating such calculations, you enhance your ability to perform dynamic data analysis tailored to specific business requirements. In this segment, we will explore how the bucket stage operates in MongoDB's aggregation framework to group sales transactions into specified price ranges. The bucket operator excels at categorizing continuous data points into defined intervals, allowing us to gain insights into how many transactions fall within each range. In our example, we set up a pipeline where we group sales amounts by the amount field. We define clear boundaries for our buckets, which are set at $0, $500, $1,000, $1,500, and $2,000. This means that any sales amount that falls between these figures will be counted within the respective buckets. Additionally, we included a default bucket labeled Other for any amounts that don't fit within the specified ranges, ensuring no data is discarded. The output of this operation specifies that we wish to count the number of documents falling into each bucket using the sum aggregation operator. Ultimately, this pipeline provides a summarized view of the number of transactions in each defined sales range, helping to quickly identify trends and patterns in sales performance. The sample operator in MongoDB allows you to randomly select a subset of documents from a collection, making it an invaluable tool for obtaining a representative sample. In this example, we are using sample within the aggregation framework to yield 5 random documents from the reviews collection. This randomness is crucial when analyzing user feedback, as it enables you to capture diverse perspectives without the bias that might come from manually selecting records or reviewing the entire dataset. The simplicity of this command belies its effectiveness. By just specifying the number of documents you want, you can gather insights efficiently. This operation highlights how MongoDB can assist in data analysis by quickly providing samples that can be further examined for trends or insights, ultimately enriching your understanding of the user experience based on a variety of reviews. Thus, Sample serves as a powerful tool to inform decision-making through data-driven insights while maintaining the integrity of randomness in your data sampling process. Let's dive into the sort by count stage, a powerful tool for quickly analyzing data within a collection. This operation counts the number of occurrences of distinct values in a specified field, which can help identify trends and distributions in the dataset. In this case, we apply it to the category field of the products collection. When you run this aggregation, MongoDB will scan through all documents in the products collection, tallying how many times each unique category appears. The results are then sorted in descending order, meaning the category with the highest count will show up first in the output. This feature is particularly beneficial when analyzing inventories or customer behaviors, as it provides a clear snapshot of which categories are most prevalent. Overall, using sort by count streamlines the process of gaining insights from your data, helping you to make informed decisions on inventory management or marketing strategies based on real-time analytics. In this section, we are leveraging the power of the lookup stage, which allows us to perform join-like operations in MongoDB, making it easier to combine data from different collections. Here, we begin by looking up customer data from the customers collection based on the customer ID field present in our orders collection. The results are stored as an array in a new field called customer info. Following the lookup, we apply the unwind stage to flatten the customer info array, effectively creating individual documents for each customer associated with an order. This ensures that we have a straightforward structure where each order document contains pertinent customer information directly, rather than nested arrays. Finally, we utilize the project stage to shape our output. We select only the essential fields, the order ID, the customer's name from the joined collection, and the order amount. This approach presents a clean and concise format, facilitating better readability and understanding of the relationship between orders and their corresponding customers, thereby enhancing the insights derived from our data aggregation. In this aggregation pipeline, we focus on analyzing employee performance metrics. We begin with the match stage, which filters the dataset to include only active employees, ensuring our analysis is relevant to current staff. Next, we use the group stage to aggregate the data by employee ID. Here, we compute total sales with the sum operator, calculate the average performance rating using AVG, and count the total number of projects completed by using another sum set to count each entry. The following stage is sort, which organizes our results in descending order based on total sales, allowing us to quickly identify top performers. Lastly, the project stage is utilized to reshape our output. This stage renames the ID field to employee ID, retains total sales and total projects, and rounds the average rating to 2 decimal places for clarity. By structuring our aggregation in this way, we create a concise and informative summary of employee performance, facilitating better insights for decision makers. In this segment of our tutorial, we leverage the powerful facet operator to conduct multifaceted analysis within a single aggregation framework operation. The code snippet effectively defines 3 separate pipelines under the facet stage. The first pipeline calculates total sales by employing the group stage to sum up the sale amounts, simplifying the process to derive the overall revenue generated from all transactions. Next, the second pipeline offers a monthly breakdown of sales. Here, we again utilize the group stage to aggregate sales data by month, identifying which months generated the highest revenue, followed by a sort stage that arranges these results in descending order of total sales. Lastly, The third pipeline focuses on product reviews, counting the number of reviews for each product using group, which helps in assessing product engagement and performance. Altogether, this approach elegantly combines insights from the same dataset, making it an ideal method for comprehensive reporting and decision-making in data analysis tasks. Each pipeline within Facet operates independently, allowing for a cohesive, detailed view of sales and reviews from a single query. As we conclude our dive into advanced aggregation techniques, remember that MongoDB's aggregation framework is a robust tool allowing you to manipulate and analyze data in ways that traditional databases may struggle with. By mastering operators like add fields, bucket, sample, lookup, and the concept of pipelines, you place a powerful weapon in your data analysis arsenal. Remember, being able to customize and effectively aggregate your collections can significantly enhance your insights and decision-making processes in any organization. Anytime you think of how to approach complex data analysis tasks, think of the aggregation framework in MongoDB first. Thank you for watching, and don't forget to try these techniques in your projects to truly grasp their potential. Happy coding! MongoDB transactions are pivotal to managing complex database operations effectively. Since the introduction of multi-document ACID transactions in MongoDB 4 in 2018, developers can now ensure data integrity and consistency across multiple documents, which is crucial for various applications. Today, we will explore what transactions are, their properties, how to implement them using MongoDB, and best practices associated with their use. So far, we've covered advanced aggregation techniques in MongoDB, emphasizing operators like add fields, bucket, and sample. Now, we will delve into transactions, focusing on the ACID properties that make them valuable for managing data integrity in database applications. In this example, we utilize MongoDB's transaction capabilities through the PyMongo library to illustrate how to maintain data integrity during complex operations. Initially, we establish a connection to the MongoDB server using Mongo Client, specifying the database where our collections are located, in this case, orders and inventory. Next, we initiate a session with the start session method, crucial for working with transactions, as it allows us to group multiple operations together. Within this session, we begin a transaction by invoking start transaction. This is significant because any operations made within this block are treated as a single unit of work. The first operation we perform is inserting a new order into the orders collection, specifying necessary details such as the SKU and quantity. Following that, we update the inventory by decrementing the quantity of the product, ensuring that the SKU exists and has a sufficient quantity available for the transaction to proceed. The use of the session parameter in both operations ensures that all changes are tracked together, facilitating rollback if any operation fails, thereby maintaining the atomicity of the entire process. Now, let's discuss the ACID properties of transactions, which stand for atomicity, consistency, isolation, and durability. Understanding these properties will help you utilize transactions effectively in your MongoDB applications. Atomicity ensures that all operations within a transaction execute completely or not at all. If one operation fails, all preceding operations are rolled back, ensuring that no partial updates occur. This property is crucial in applications like financial services, where even a minor error can lead to significant issues. Consistency guarantees that transactions bring the database from one valid state to another. After a transaction is completed, all data must adhere to all defined rules and constraints. This principle prevents data corruption and anomaly, where the database can end up in an invalid state if some operations succeed and others fail. Now, isolation ensures that transactions do not interfere with one another. It prevents concurrent transactions from seeing each other's intermediate states, which can lead to inconsistencies. For example, if two transfers from the same account occur simultaneously, and if isolation is not maintained, one transfer might affect the balance evaluated by the other, resulting in incorrect deductions. Lastly, durability guarantees that once a transaction is committed, it remains so, even in the case of a system failure. This implies that the outcome of a transaction is recorded in permanent storage, and recovery processes after a crash will still reflect the changes made by committed transactions. In this section, we will explore how to initiate transactions in MongoDB using the PyMongo library. First, we begin by creating a session with the startSession method, which allows us to manage a series of operations within a transaction. Defining transaction options is also crucial. For instance, specifying read preference. Primary ensures that the transaction reads data from the primary replica, while read concern and write concern help manage data integrity and durability during the transaction. As we enter the transaction context with start transaction, we can perform our desired database operations. Within this block, we can execute multiple operations, such as inserts or updates, which will be atomic in nature. If any operation fails, the entire transaction will roll back, maintaining data consistency. The flexibility in customizing transaction options gives developers better control over how these transactions will behave under various scenarios. This code snippet neatly encapsulates the critical components of managing transactions, ensuring that we follow the best practices for transaction management in MongoDB applications. In the following code, we implement a function that facilitates user reservations while adhering to the principles of transactions in MongoDB. First, the function establishes a connection to the user and listings collections in the sample AUM database and initiates a new session to begin transaction management. Within the transaction, we update the user's reservation list and the listings dates reserved. The update1 method is called on both collections, ensuring any added reservation dates are unique to prevent conflicts. Conditional checks follow the update operations. If the user's email is not found, an error is thrown, ensuring that operations only proceed if the user exists. Similarly, if a listing is already booked for the desired dates, the function responds accordingly by aborting the transaction and rolling back changes to maintain data integrity. This approach exemplifies how transactions can be used to ensure that complex operations, such as booking accommodations, are handled safely and consistently, preventing data anomalies within the application. By handling reservations in this way, we safeguard against double bookings and reinforce reliable data management practices in our application. In conclusion, transactions add a powerful layer of reliability and control within MongoDB's already flexible data model. They are instrumental in enforcing integrity and consistency across multiple operations, making your applications robust and dependable. As you've learned today, understanding and correctly implementing transactions will allow you to create applications with higher reliability, a critical factor as systems grow more complex. So, be sure to consider ACID properties, utilize the right APIs for transaction management, and steer clear of the limitations inherent to transactions in your MongoDB setup. Make sure to put this knowledge to practical use and further explore MongoDB's transaction capabilities as they continue to evolve and support even more sophisticated data management strategies. Thank you for joining me on this exploration of transactions in MongoDB. Let's venture deeper into these concepts in our future discussions. In this section, we'll dive deep into the advanced implementation of transactions in MongoDB. You'll see how to integrate these powerful features into your applications for enhanced data integrity and consistency. So far, we learned about the importance of transactions in MongoDB for ensuring data integrity and consistency across operations. We explored the ACID properties of transactions: atomicity, consistency, isolation, and durability, highlighting their significance in application development. Additionally, we discussed how to implement transactions, the limitations associated with their use, and practical examples demonstrating their value in real-world scenarios. Understanding these concepts will empower you to build robust applications using MongoDB. Now, we will cover advanced transaction implementation techniques that will help enhance your application's user experience and reliability. In this part of the tutorial, we focus on implementing error handling in transactions using MongoDB. The code begins by establishing a connection to the MongoDB server and defining two collections, one for orders and the other for inventory. The process_auto function encapsulates the transaction logic. Within this function, a session is initiated, and a transaction is started for processing an order. The first step in the transaction involves inserting the order into the orders collection. If this operation is successful, the code then attempts to update the inventory by decrementing the quantity of the specified stock item. However, to ensure reliability, the code includes error handling mechanisms using try-except blocks. If a connection or operation failure occurs, the transaction is aborted and an error message is printed, allowing you to take further actions, like notifying users or implementing a retry strategy. This not only reinforces data integrity through effective error management, but also enhances the overall user experience by ensuring that errors are handled gracefully and do not leave users in uncertainty. Thus, the code demonstrates a critical aspect of robust application development using MongoDB transactions. In this code segment, we implement transactions in a sharded MongoDB cluster using the PyMongo driver, emphasizing the importance of session management and transaction configurations. After establishing a connection to the MongoDB server, we initiate a session, which allows us to group multiple operations into a single transaction. Here, we define transaction options, including read and write concerns, to ensure that all our operations meet specific criteria regarding data visibility and acknowledgement. Within the try block, we start the transaction and perform operations on sharded collections, specifically inserting an order into the orders collection and updating the corresponding inventory in the inventory collection. Each of these operations is associated with the session, ensuring they are included in the transaction context. If everything goes as planned, we commit the transaction, making all changes permanent. However, if an error occurs, we catch the exception, abort the transaction, and print the error message, preventing any partial updates that could compromise data integrity. Finally, we wrap up the session, ensuring that resources are cleaned up properly. This approach helps maintain the integrity and consistency of our applications' data across multiple shards. In this section, we explore the implementation of a transaction retry mechanism when processing orders in MongoDB. The code defines a function called process_auto_retry, which attempts to process an order multiple times if transient errors occur, such as connection failures or operation failures. The function begins by initiating a session and specifying transaction options, including read and write concerns to ensure reliable operations. Inside a loop that runs for a predetermined number of retries, the function starts a transaction and tries to insert the order into the orders collection and update the inventory collection concurrently. If successful, the transaction is committed and a success message is returned. However, if an error occurs, the transaction is aborted and the code checks if additional attempts are allowed. For retries, the code implements a basic backoff strategy, pausing briefly before the next attempt and logging an error message to inform the user. Should all retries fail, a message indicating the ultimate failure to process the order is returned. This mechanism enhances the application's resilience against temporary disruptions, helping ensure successful transaction processing. This code showcases an efficient method for updating inventory and processing orders using transactions in MongoDB. It begins by establishing a session, allowing us to execute a series of operations that can either be committed as a whole or rolled back in case of failure. The transaction is initiated using session start transaction, ensuring that all subsequent operations occur within this transactional context. Next, the code retrieves the order details based on the provided ordered. It checks whether there is sufficient inventory for the requested quantity, raising a value error if stock is inadequate, which would trigger an abort of the transaction. If the inventory check passes, the order status is updated to processed, and the inventory is decremented accordingly with the specific quantity. By using the same session across these updates, we ensure that either both operations succeed or none at all, maintaining data integrity. If any part of this process encounters an issue, the transaction is aborted, meaning that any changes made are rolled back, thus preventing unwanted modifications in the database. Finally, the session is concluded, demonstrating proper resource management. This code effectively illustrates best practices in MongoDB transaction handling, optimizing performance and reliability. In this example, we are accessing transaction statistics using the service status command in MongoDB to gain insights into transaction performance. The script begins by establishing a connection to the MongoDB server with the provided connection string, which refers to a local instance running on the default pod. Next, we define the database we are working with by assigning it to a variable. The heart of the code lies in executing the service status command on the database, specifically targeting the transactions section of the output. This section provides valuable insights, including the current number of active transactions, total commits, and rollbacks, which are crucial for analyzing database performance. By printing the transaction statistics, we can quickly assess the performance metrics of our transactions, helping us identify potential bottlenecks in our operations. Regular monitoring of such statistics is essential for maintaining optimal performance and ensuring that transaction behaviors align with our expectations. This practice allows developers to make informed decisions and adjustments to enhance overall database operations. As we wrap up our exploration of advanced transaction implementation, it's clear that leveraging the power of transactions in MongoDB is more than just executing a set of operations. It's about building a robust system that can withstand failures and run efficiently under various conditions. From understanding error handling and retry logic to optimizing the scope and monitoring performance, the techniques discussed today will help elevate your MongoDB applications to new heights. By incorporating these practices, you're not solely maximizing the potential of MongoDB's transaction capabilities, but also enriching your application's reliability and user experience. Keep experimenting with these strategies, and you'll find that transactions can be a game changer in your software development journey. Thank you for tuning in. I hope you feel inspired and equipped to implement these advanced transaction techniques into your projects. Every database system, whether relational or non-relational, relies on indexing to speed up data querying. Indices are like the table of contents in a book, allowing you to locate information quickly without having to flip through every page. In this lesson, we will explore what indexes are, why they are crucial for efficient data retrieval, and how to implement them using various database systems. So far, we learned about the significance of transactions in MongoDB, focusing on their ACID properties and how they contribute to data integrity and consistency. We discussed practical implementations of error handling, transaction management in sharded clusters, and retry mechanisms to enhance application resilience. Additionally, we covered best practices for minimizing lock contention and optimizing transaction performance. Now we will delve into the world of indexes and how they can transform the way we interact with data. Creating an index on a specific column is a fundamental step in optimizing database performance. The command createIndex IX email on customers email is used to build an index named IX email on the email column within the customers table. By doing this, the database organizes the entries based on the values in the email column, resulting in a much faster retrieval process for queries that search for customers by their email addresses. When a search is conducted using the email address, the database engine utilizes this index to quickly navigate to the corresponding record, instead of engaging in a full table scan, which would check every record sequentially. This efficiency is particularly vital as your dataset expands, potentially containing hundreds of thousands of records. Ultimately, this index enhances performance and reduces query response times, showcasing the critical role of indexes in effective database management. The code illustrates a simplified representation of how a B-tree data structure organizes index entries. In this diagram, we have a balanced tree with a root node containing the value 20, which serves as a pivotal point for navigating through the tree. The left and right subtrees represent age values less than and greater than 20, respectively, with child nodes further subdividing the data. As you can see, the left branch contains values 15, 10, and 18, while the right branch includes 25, 22, and 30. This hierarchical structure allows the database to perform efficient searches. When querying for records, such as customers of a specific age, the database starts at the root node and moves downwards, comparing the searched value to determine which child node to follow next. This method significantly reduces the number of comparisons needed, allowing for faster data retrieval as it narrows down the search path with each step taken within the tree. By leveraging this method, the database efficiently locates relevant records without scanning all entries, thereby optimizing query performance. In this section, we will examine how data is inserted into a database using SQL commands, specifically focusing on adding a new customer to the Customers table. The SQL command we use is the insert into statement, which is fundamental for inserting new records into a specified table. The command specifies the target table, in this case, customers, and defines the columns where the data will be inserted: name, email, and age. By providing the corresponding values such as John Doe for the name, john@example.com for the email, and 30 for the age, we create a new entry in the Customers table. However, it's crucial to understand that alongside this insertion, the database must also update any indexes associated with the affected columns. This ensures that future queries can efficiently retrieve data based on these fields. Therefore, while the command successfully adds a new customer, it also demonstrates the underlying mechanism where the database maintains performance through indexing, balancing the benefits of read operations against the overhead incurred during writes. Creating indexes is vital for optimizing query performance in databases. In the given examples, we create indexes on specific columns of the Customers table. The first two commands illustrate how to create standard indexes on the last name and age columns. By creating these indexes, the database can quickly locate records based on these frequently queried attributes. Implementing indexes on columns that appear in where clauses helps reduce the amount of data the database engine needs to scan, thus speeding up query execution. The second command demonstrates how to create a unique index on the email column. This unique index ensures that all entries in the email field remain distinct, preventing any duplicate email addresses from being stored in the table. This is particularly important for ensuring data integrity, especially in contexts where email addresses are used for user identification or communication. Together, these indexing strategies highlight the balance needed between performance enhancement and maintaining data quality within a database. In this section, we will explore how to create a composite index, which is particularly useful for optimizing queries that rely on multiple columns for filtering. The command provided creates an index named age on the last name and age columns of the Customers table. Creating this composite index is beneficial because it allows the database to efficiently retrieve records based on a combination of last names and ages. This means that queries which search for customers by both criteria will execute faster, as the database can utilize the index to bypass irrelevant rows. It's important to note that the order of the columns in the index matters. In this case, the database will first sort by last name and then by age. Therefore, when designing your indexes, always consider the typical query patterns users employ. If users often search for customers by last name and age together, this composite index can substantially enhance performance. Overall, implementing such indexes can lead to a more responsive system, ultimately improving the overall user experience. In this example, we are focusing on creating an index in a MongoDB collection to enhance query performance. The command db customers create index email 1 is a straightforward yet powerful way to optimize how we access customer data. By specifying the email field and setting its value to 1, we are instructing MongoDB to create an ascending index on this field. This ascending order means that the database will sort the entries in the index from the lowest to highest email values. Such an index allows MongoDB to quickly locate documents based on the email field when executing queries. Rather than scanning through every document in the customer's collection, MongoDB can leverage this index to jump directly to the relevant entries, drastically reducing the time needed to find a specific email. Furthermore, using indexes effectively can also promote better performance in larger datasets, where operations could otherwise become time-consuming. As a result, implementing this index not only enhances data retrieval speed, but also improves the overall efficiency of interacting with customer records in the database. To maintain optimal performance in your database, it's essential to regularly address index fragmentation. The command here, alter index all ON customers rebuild, plays a critical role in this maintenance task. When you execute this command, it rebuilds all the indexes on the customers table in your SQL Server database. Rebuilding an index means that the database reorganizes its internal structure for each index, often using a B-tree format, thus eliminating fragmentation. Fragmentation can occur over time as you add or remove records, making the index less efficient and causing slower query performance. By running this command, you ensure that the indexes are kept up to date and perform optimally, enabling the database to quickly access records without unnecessary overhead. Regular index maintenance, such as rebuilding or reorganizing indexes, is vital, especially as your database grows. This practice enhances the overall responsiveness of your database environment, ensuring that it can handle increased loads efficiently and effectively. Thus, incorporating such maintenance steps into your routine can significantly improve your database's performance and reliability. In conclusion, indexes play a significant role in maximizing data retrieval efficiency within databases. They provide quick access paths to data, allowing for rapid query execution. While they come with trade-offs concerning write operations and storage, proper index strategy can lead to improved application performance. So far, we've covered what indexes are, how they work, when to use them, and how to manage them effectively. In the next lesson, we will introduce the concept of normalization and its impact on database design. Indexes are a fundamental part of database management systems, and understanding their various types is crucial for efficient data retrieval. In this session, we will delve into the different index types and the strategies for their optimal use, helping you become more proficient in database performance optimization. So far, we have learned about the importance of indexing in databases, which speeds up data retrieval by reducing the number of records examined. We explored how to create and use indexes in both SQL and MongoDB, highlighting their structure, types, and trade-offs regarding write operations. Additionally, we discussed when to implement indexes effectively and the significance of maintaining them to optimize performance. Now we will talk about the different types of indexes and how to choose the right ones for your specific needs. Creating a single-column index in SQL is a straightforward yet crucial step in optimizing query performance for specific data retrieval tasks. The command, which begins with create index, sets up an index named IG's last name on the last name column of the customer's table. By executing this command, you're instructing the database to construct a structure that allows for faster lookups on the last names of customers. Instead of scanning the entire table for matches during searches, the database can now utilize this index to directly locate the relevant records, significantly speeding up the search process. This approach is particularly beneficial when queries frequently filter or sort data based on the last name, making it an essential tactic for improving database efficiency. It enhances performance without altering the underlying table data, allowing for seamless and quick access to specific rows as needed. This indexing technique is vital in scenarios where rapid data retrieval is necessary, ensuring that your database performs optimally under various querying conditions. When creating a composite index to optimize the performance of queries involving multiple columns, consider the command that specifies both columns of interest. The command initiates the creation of an index named age on the customer's table, focusing on the last name and age columns. By incorporating both fields into the index, the database is equipped to execute searches that filter based on these combined attributes much more efficiently. This is particularly useful if your queries frequently involve retrieving customer records, where both last name and age are conditions for filtering. The fundamental advantage of a composite index lies in its ability to streamline the searching process, reducing the time spent scanning through records without this optimization. As a result, when you run queries that reference both the last name and age, the database leverages the structure of the composite index to locate relevant records swiftly. Understanding the utility of such composite indexes is crucial for enhancing query performance and can significantly contribute to overall database efficiency in data retrieval scenarios. Creating a unique index is a critical step in ensuring data integrity within a database. In this case, we are focusing on the email field in the customers table. By implementing a unique index with the command provided, we guarantee that every email address stored is distinct across all records. This means that the database will reject any attempt to insert a duplicate email, preventing errors that could lead to user confusion or data inconsistencies. This unique index not only enhances the quality of the data by eliminating redundancy, but also optimizes how we can query that information later. When a search for an email is made, the database can quickly locate the record without needing to sift through duplicates. Overall, the implementation of unique indexes serves as a foundational practice in database management, reinforcing the principle that safeguarding data integrity is as important as improving query performance. By ensuring that critical fields like email addresses remain unique, we create a more reliable and user-friendly database environment. Creating a full-text index is a powerful way to enhance search capabilities within text-based columns of your database. In the provided SQL statement, we are defining a full-text index on the content column of the articles table. This specific command links the full-text index to a primary key index, denoted by key index pk article ID, which ensures efficient lookup of the index data. The addition of with change tracking auto enables the index to automatically update as records in the articles table are modified. This feature is crucial for maintaining the accuracy of the full-text index, allowing users to execute text-based queries, like searching for an article containing a specific term, without the need for constant manual updates. Consequently, instead of scanning the entire content of the articles, the database can quickly access the index terms, significantly improving performance and enabling complex search operations for better user experiences. In this section, we will look at how to create a non-clustered index using SQL, which helps improve the speed of queries that involve sorting or filtering based on specific columns. The code presented creates a non-clustered index named IGS on the customers table, utilizing both the last name and first name columns in ascending order. A non-clustered index is particularly advantageous because it creates a separate structure that references the original data without rearranging it, allowing for efficient access while maintaining the original order of entries in the table. By indexing both last name and first name, the database can quickly locate records that fulfill queries filtering or sorting based on these names. This is especially useful in scenarios where you frequently search for customers by their names, as it significantly boosts query performance and reduces the time the database takes to return results. Ultimately, implementing such an index ensures a better user experience by decreasing wait times during data retrieval operations. In the context of optimizing database performance, creating a bitmap index is a powerful technique for improving query efficiency, especially for columns with a limited number of distinct values. The code snippet provided demonstrates how to create a bitmap index on the status column of the user's table, specifically naming the index IDEX user status. A bitmap index works by utilizing a bitmap for each distinct value in the column it indexes, which significantly speeds up query processing for filtering operations that depend on these values. In scenarios where the status column comprises a few distinct entries, like active and inactive, the bitmap index can reduce storage costs and enhance the speed of operations that filter users based on their status. This kind of indexing is particularly beneficial for analytical queries, where quick access to data based on categorical values is necessary. By using a bitmap index, the database can efficiently manage large datasets while still maintaining swift response times when executing queries that involve these limited value columns. As we can see, different types of indexes come with their own set of advantages, tailored for specific use cases. However, it's essential to consider the trade-offs involved with each index type. Adding indexes can improve read performance but might negatively impact write operations. Every time you insert, update, or delete data, the indexes must also be updated. To manage this, it's crucial to analyze and design your indexing strategies based on the specific query patterns of your application. To effectively monitor the usage and performance of your indexes in SQL Server, you can utilize the sys DMDB Index Usage Stats view. This particular query is designed to retrieve index usage statistics specifically for a table identified as customers. When you call object ID customers, the query fetches the object ID of the customers table, allowing SQL Server to track the index statistics associated with that specific table. The output provides valuable insights, including how many times each index on the customers table has been used for read operations, like seeks and scans, as well as write operations, such as updates and deletes. By analyzing this data, you'll be able to understand which indexes are actively contributing to query performance and which might be unnecessary or redundant. This proactive approach, combined with regular monitoring, ensures that your indexing strategy remains optimized according to your application's specific needs, ultimately aiding in better performance and efficiency in database management. Maintaining indexes is crucial for ensuring optimal database performance over time. The command to rebuild an index is a fundamental tool in SQL Server that addresses index fragmentation, which can occur as data changes over time. By using the command to alter the index on the customers table, you're instructing the database to restructure all existing indexes for that table. This process enhances efficiency by effectively reorganizing the internal data structures, which can become disordered as records are added, updated, or deleted. Think of this operation as a digital spring cleaning. Just as a well-organized closet allows for easier access to your belongings, a well-maintained index speeds up data retrieval processes. After executing this command, subsequent queries targeting the customers table will benefit from improved performance, as the database can now quickly navigate through the freshly optimized index structure to find the necessary records without unnecessary delays. Regularly performing this maintenance task helps maintain the overall health of your database, ensuring it runs smoothly and efficiently. In summary, understanding the various types of indexes and their optimal use strategies is key to maximizing database performance. By leveraging single-column, composite, unique, and specialized indexes appropriately, you can ensure that your data retrieval processes remain fast and reliable. Furthermore, Maintaining these indexes and being aware of their implications on write operations will position you ahead in managing your database efficiently. So, keep analyzing, keep learning about your specific scenarios, and adapt your strategies accordingly. In the next session, we will dive into the concept of normalization and its significant impact on database design. Welcome to this tutorial on MongoDB Atlas, the cloud-based database service that is revolutionizing how developers manage their data. It's not just a simple database service, it's a robust and comprehensive solution crafted specifically for modern application demands. If you're looking to simplify and enhance your data management, keep watching. So far, we covered the essential role of indexes in database management, diving into how they boost data retrieval speeds and maximize performance. We discussed various index types, such as single-column, composite, unique, and specialized indexes, and even touched on their creation syntax in SQL. Additionally, we explored how to analyze usage statistics and maintain indexes effectively to counter fragmentation and improve performance. Now, we will shift gears and talk about MongoDB Atlas and its capabilities for modern application development. Let's start by understanding what makes MongoDB Atlas a go-to choice for developers. MongoDB Atlas is essentially a database as a service, DAR-S, platform that is built on the infrastructure of major cloud providers such as AWS, Google Cloud Platform, and Microsoft Azure. This multi-cloud compatibility affords users significant flexibility in their data management strategies. You can scale your database easily across more than 95 cloud regions, which distinctly enhances your control over data management while ensuring high availability. With just a single command, you can effortlessly create a new MongoDB cluster, which is a foundational step for any developer looking to leverage the power of MongoDB Atlas. The command specifies a few critical parameters: the name of the cluster, the region where it will be hosted, and the tier of service. In this case, the cluster is called My Cluster, indicating that it's the identifier you'll use for future references. By choosing the US East 1 region, you ensure proximity to your user base, which can help enhance performance and reduce latency. The M10 tier designation means that you'll have a dedicated instance that can handle moderate workloads, making it suitable for startups or projects requiring speedy deployment without sacrificing performance. By utilizing the command line interface, you gain a quick and efficient way to set up your database infrastructure, allowing you to focus more on developing your application and less on the complexities of traditional database setup processes. This ease of use contributes greatly to the overall appeal of MongoDB Atlas, making it an excellent choice for both novice and experienced developers alike. Part of the comprehensive nature of MongoDB Atlas is its focus on automating routine tasks. It manages crucial aspects of database management, such as software patching, hardware provisioning, and backups. This means that as a developer or a DevOps engineer, you can focus entirely on building your applications rather than worrying about the infrastructure. Compatibly, it allows for automated scaling, which adjusts database resources according to real-time demand. Let's say your application encounters a spike in traffic. The system automatically scales up resources without any downtime, providing a seamless experience for your users. Here is how you would configure auto-scaling in your Atlas UI. 1. Navigate to your cluster settings in the MongoDB Atlas UI. 2. Find the auto-scaling option and toggle it on. 3. Set parameters for when to scale up or down based on CPU or memory utilization. With this feature in place, you can ensure consistent application performance without needing constant manual interference. To illustrate the backup restoration feature in MongoDB Atlas, consider the command for initiating a restoration of a specific cluster snapshot. This command allows you to efficiently recover your database to a previously saved state, which is crucial for safeguarding against data loss or corruption. In this command, the cluster option specifies the identifier of your cluster, ensuring that the restoration is accurately directed to the desired database instance. The snapshot parameter is equally important as it denotes the exact snapshot from which you want to restore your data. By providing this information, MongoDB Atlas can precisely execute the restoration process, making it seamless and quick for developers. This functionality not only emphasizes the platform's robust backup capabilities, but also instills confidence in your data management strategies. Utilizing this command ensures that a significant degree of control and efficiency is maintained during the recovery process, allowing developers to focus on building applications without the constant worry of data integrity. In this section, we'll explore how to configure role-based access control, RBAC, in MongoDB Atlas using a straightforward JSON format. The code snippet provided authorizes a user named developer with the role of read-write for access to my database. This configuration is crucial for managing user permissions within your database environment. By assigning the read-write role, you are enabling the user to both read data from and write data to the specified database, allowing for necessary interactions while maintaining security protocols. Properly managing user roles helps prevent unauthorized access and ensures that each user has only the permissions required for their tasks. It illustrates a principle of least privilege, a best practice in security management. Additionally, you can expand this setup by defining more roles or databases as your application evolves, thereby maintaining a secure environment even as user requirements change. Understanding how to effectively utilize RBAC is essential for safeguarding your data while leveraging the collaborative capabilities of MongoDB Atlas. To enable query profiling in your MongoDB Atlas cluster, you can utilize a specific command in the Atlas CLI. This command is designed to turn on profiling for all queries within your selected cluster, allowing you to gather crucial performance data about your database operations. By setting the profiling mode to all, you activate comprehensive logging of query execution details. This mode provides insights into how long queries take to execute and the CPU resources they consume, which is vital for identifying poorly performing queries. Such analytics empower developers to optimize data access patterns, leading to enhanced application performance. Regularly reviewing profiling data can help you refine your queries over time, adapting to evolving application needs and usage patterns. Ultimately, enabling query profiling is a proactive step that not only offers visibility into your database's operational efficiency, but also aids in sustaining optimal performance as your application scales and user demands fluctuate. It's a best practice for any developer looking to maintain a high-performing data environment in MongoDB Atlas. Now, speaking of efficiency, let's highlight the capabilities of MongoDB Atlas for working with unstructured data, which is increasingly common in today's applications. Atlas allows for big data processing and integrates seamlessly with tools for data analysis. The Atlas Data Lake, for example, provides the ability to bring in and analyze data from different sources, all while allowing you to use familiar MongoDB queries. You can set it up simply by indicating what data sources you'd like to integrate through the Atlas UI, allowing you to extend your application's functionality without extensive rework. It's a powerful way to streamline your data processing pipelines. In summary, MongoDB Atlas is a feature-rich platform that not only simplifies database management, but also enhances scalability, security, and efficiency. This innovation caters to modern application demands and allows developers to focus on what really matters, creating incredible software solutions. So far, we covered the essential features of MongoDB Atlas, including its automation capabilities, security measures, performance monitoring, and big data processing. We've shown how to set up clusters, manage backups, and implement security protocols. In our next session, we will delve deeper into the advanced data processing techniques provided by MongoDB Atlas, such as data federation and real-time analytics. Make sure to subscribe to catch all updates and happy coding. In this lesson, we will explore advanced features of MongoDB Atlas, particularly focusing on how these features can enhance your data management and retrieval processes with ease and efficiency. So far, we have learned about the key features of MongoDB Atlas, emphasizing its role as a comprehensive database as a service that enhances scalability, security, and efficiency for developers. We explored its automation capabilities, security measures, performance monitoring, and integration for big data processing. Now, we will dive into advanced data processing techniques provided by MongoDB Atlas that make handling complex data scenarios a breeze. In this section, we'll delve into how to store and query vector data using MongoDB API for image processing applications. The first step demonstrates how to insert a document into the images collection. This document contains a name attribute as well as an image data field, which stores a high-dimensional vector that represents the characteristics of an image. The vector's structure allows it to encapsulate various features of the image, serving as a crucial element for later retrieval and similarity searches. Moving on to querying, we define a query vector intended to find similar images. The usage of the near operator is pivotal here, as it facilitates the search for documents whose vectors are geographically close to the specified query vector. The geometry field is set to define the type and coordinates of our vector, while max distance indicates the allowable variance from the query vector, which ensures that the results returned are not only relevant, but also within a defined proximity. This capability is essential for applications such as image recognition or recommendation systems, providing a powerful means to extract similar content from extensive datasets effectively. To enable full-text search capabilities in MongoDB, the first step is to create a text index on the collection that holds the text data. In this example, we are using the createIndex method on the posts collection, specifying that the content field should be indexed for text search. This index allows MongoDB to efficiently process queries that search through the text, making retrieval of relevant documents much faster. Once the index is established, you can run sophisticated search queries. The demonstrated example employs the text operator, which allows you to search for posts containing specific terms, in this case, database and MongoDB. This query benefits from the text index to return suitable results quickly. Additionally, to enhance the search experience, you can introduce relevant scoring by sorting the results based on how closely they match your search terms. The example illustrates using the sort method with the score meta field to rank the documents accordingly and limit the number of displayed results. This approach not only streamlines the user's search experience, but also ensures they receive the most pertinent content for their queries. In this section, we focus on utilizing Atlas Data Lake for effective data analytics across different storage locations. First, you need to define your data sources, allowing Atlas Data Lake to understand where to retrieve your data. In the example, we configure an S3 bucket as the data source by specifying the bucket name and the path to the data files. This setup is crucial as it establishes a seamless connection between your cloud storage and MongoDB, enabling integrated queries. Next, after the data source is configured, you can run complex queries against the data stored in the S3 bucket. The aggregation query provided filters the documents to include only those in the technology category, grouping them by authors to count the number of posts attributed to each. This method not only helps in summarizing data, but also provides insights into content creation across different authors, thus facilitating a comprehensive understanding of the data landscape without requiring cumbersome data migrations. By leveraging Atlas Data Lake, you can unify your data analysis process and gain enriched insights directly from mixed data sources. To utilize change streams effectively, you start by creating a change stream cursor on the orders collection, which allows your application to react in real time to any changes. The code snippet demonstrates this by invoking the watch method on the collection, resulting in a change stream that monitors all operations. Once the change stream is set up, you can listen for changes through the on method, which takes a callback function as an argument. This function receives a change object whenever an update occurs, allowing you to handle the change accordingly. In the example, when an order is updated, the change object is logged to the console, providing insights into the specific details of the modification. This setup not only enables user notifications about status changes, but also enhances user engagement by maintaining up-to-date data views without needing constant polling. By leveraging change streams, you can build more interactive applications that respond dynamically to database changes, offering a seamless experience for users as they stay informed about the latest developments in the application. This method significantly improves responsiveness and ensures data accuracy. In the following code snippets, we will explore how to efficiently utilize MongoDB's aggregation framework to analyze data within a collection. The first example demonstrates a basic use of the group stage to calculate the average salary of employees, grouped by their departments. In this code, we first specify the collection we want to aggregate, which is employees. We then define the group operation, where the id property is set to the department field, allowing MongoDB to group the salary data by department. The average salary field is computed using the AVG operator on the salary field, which automatically computes the average salary for each department group. In the second example, we expand on this by not only calculating the average salary per department, but also counting the total number of employees in each group. Here, we add an additional field called employee count, utilizing the sum operator to count each document in the group. This enhanced aggregation provides deeper insights, allowing for better reporting and analytics that can be valuable for organizational decision-making and resource allocation. Finally, let's talk about the integration capabilities of MongoDB Atlas with third-party tools and services. This means you can connect Atlas with various applications, either for data visualization, management, or processing. For instance, with tools like Tableau or Grafana, you can visualize data stored in your MongoDB collections directly. The connection is usually managed through standard ODBC or JDBC drivers, allowing seamless interaction between Atlas and visualization tools. Here's a brief example of how you might prepare your MongoDB for visualization. 1. Navigate to the Atlas UI and select your cluster. 2. Locate the Connect section and choose the Connect Your Application option. 3. Copy the connection string provided in the dialog box. Using this connection string in visualization tools will allow you to pull data from your database directly. For example, if you paste it into Tableau, you can easily visualize your employee data, order statistics, or any other valuable insights derived from your collections. The ability to integrate with multiple services holds immense value as it expands the horizons of how data is utilized across your organization. In summary, the advanced features of MongoDB Atlas, including Atlas Vector Search, Atlas Search, Data Lake, change streams, and the powerful aggregation framework, provide developers with robust tools to manage and analyze complex datasets seamlessly. These features allow for real-time applications, sophisticated data manipulations, and the smooth integration of diverse data sources, making MongoDB Atlas a go-to choice for modern database management. As we wrap up this session, remember that understanding and utilizing these advanced capabilities can significantly enhance your development process, leading to more efficient applications and better data management practices within your workflows. Happy coding! Effective monitoring and backup are essential when deploying MongoDB in a production environment. These processes play a crucial role from the very start, fostering performance optimization and troubleshooting as you scale up your database. Just like a seasoned sailor keeps a steady eye on the horizon for storms, as a developer, you need to monitor your database's health and ensure your backup strategies are robust. Think of monitoring as your database's most reliable set of binoculars, allowing you to spot potential issues before they escalate into significant problems. So far, we learned about the advanced features of MongoDB Atlas, including Atlas Vector Search and enhanced full-text search capabilities. We explored Atlas Data Lake for seamless data querying across various sources, as well as the use of change streams for real-time updates. With these insights, developers can efficiently manage and visualize complex datasets. Now, we will cover the essential foundations of monitoring and backups in MongoDB that can help you ensure your system continues to run smoothly and securely. To effectively monitor your MongoDB instance, you can utilize two essential commands, mongostat and mongotop. The mongostat command provides a quick overview of the status of your MongoDB instance, presenting vital statistics such as the number of operations per second, memory usage, and network traffic. By running this command, you can easily gauge the health of your server, identifying any significant fluctuations or issues that may require further investigation. On the other hand, mongotop focuses specifically on monitoring the read and write activity of your collections in real time. It displays the amount of time spent reading and writing data to your collections, allowing you to pinpoint which areas may be experiencing high contention or slow response times. This command is particularly valuable during peak usage periods, as it helps you detect potential bottlenecks and enables you to make informed decisions about resource allocation or optimization to maintain optimal performance. Incorporating these tools into your monitoring routine is crucial for maintaining efficient database operations and troubleshooting any arising issues proactively. To keep track of memory usage and understand the efficiency of your MongoDB deployment, you can utilize the db server status mem command. This command retrieves essential metrics about the memory consumption of your MongoDB instance, specifically focusing on both resident and virtual memory. Resident memory refers to the amount of RAM currently utilized by the MongoDB process, while virtual memory encompasses all memory allocated to the process, whether it's actively in use or not. The information provided by this command is vital for assessing whether your working set, the subset of data you frequently access, can fit comfortably within your available RAM. Ideally, you want to ensure that resident memory usage remains below 80% of your total RAM to avoid triggering performance penalties due to excessive page faults. Keeping a close eye on these memory metrics allows you to optimize performance, diagnose potential bottlenecks, and make informed decisions about resource allocation or hardware upgrades as your dataset grows. Monitoring page faults in MongoDB is essential for understanding how well your database handles memory. The command db admin command service status 1 extra info page faults retrieves the current number of page faults that have occurred since the server started. A page fault indicates that the database needs to access data from disk because it isn't currently in memory, which can introduce latency. If you notice a rising trend in page faults, it may signify that your working set exceeds the available RAM, leading to performance degradation. In this command, db admin command service status 1 sends a service status request, which returns a comprehensive overview of your MongoDB instance's health and metrics. By drilling into extra info page faults, you're specifically honing in on the page fault metric. Keeping a close eye on this information is crucial. A high count of page faults typically suggests that you might need to optimize your memory allocation or consider upgrading your RAM to enhance overall system performance and responsiveness. Such proactive monitoring allows you to maintain a robust database environment, ensuring smooth and efficient operations. To diagnose slow queries in your MongoDB instance, you can utilize the explain method with the execution stats verbosity level. This command provides a detailed breakdown of how your query is executed, revealing essential information about the performance characteristics and index usage. When you run the db collection, find, explain, execution stats command, MongoDB first evaluates the query and generates an execution plan showing how it retrieves the data. Analyzing the output allows you to see crucial metrics, such as the number of documents examined versus the number of documents returned, which directly impacts query performance. If the output indicates that a large number of documents are being scanned for a small result set, it suggests potential inefficiencies in your indexing. This may prompt a need to optimize your indexes or to create new ones tailored to your query patterns. By addressing these inefficiencies, you can significantly enhance the speed of your queries, ensuring a smoother and more responsive experience for users interacting with your application. Thus, leveraging the explain functionality is a fundamental step in maintaining an efficiently running MongoDB environment. To initiate a backup of your MongoDB instance, the command mongodump outpath to backup is used. This command effectively creates a snapshot of your database at a specified location, securing your data against potential loss or corruption. The out parameter designates the path where the backup files will be stored, allowing for easy organization and retrieval later on. It's essential to remember that although MongoDump is a powerful tool for conducting backups, it is most effective when executed during periods of low database activity. This is primarily because the backup process can lock data, temporarily hindering performance. Regular backups are a fundamental aspect of a robust data management strategy, ensuring that you have a reliable point from which to restore in case of unexpected failures. By leveraging this command, you lay the groundwork for a comprehensive backup strategy, supporting data integrity and quick recovery. It is a crucial habit to develop in your MongoDB practice, ultimately contributing to a healthier and more resilient database environment. To create a backup of your MongoDB database while ensuring you can restore it to any point in time, you can use the mongodump command with the oplog option. This command not only captures the data in your database, but also includes the operation log, or oplog, which records all changes made to the data. By incorporating the oplog, you allow for incremental backups, meaning that you can effectively capture only changes since your last full backup, which saves time and storage space. When invoking this command, you need to specify the output directory using the out flag, which serves as the destination where the backup files will be stored. This approach is highly recommended for maintaining data integrity, especially in production environments, as it allows for point-in-time recovery. Following this process, you can seamlessly restore your data using the mongostore command, ensuring minimal disruption and maximum resilience against data loss. This not only safeguards your data, but also supports the overall robustness of your MongoDB deployment. Involving tools such as MongoDB Cloud Manager or Ops Manager can streamline the backup process. They provide sophisticated backup features that allow snapshots of your data at various intervals without you having to manually initiate each backup. These types of tools integrate seamlessly with environments running on major cloud providers, ensuring a smoother setup process. To restore a backup in MongoDB, you will utilize the mongostore command. This command is essential for bringing your data back to life when needed, ensuring that your backup strategy is effective and reliable. In the command, mongostore db testdb path /to /backup /testdb, the db flag specifies the target database for the restoration process. In this case, it's targeting the database named testdb. The path provided points to the location of your backup files, allowing MongoDB to retrieve the necessary data for restoration. It's crucial that the specified path correctly reflects where your backup was stored. When executed, this command restores the backup into the specified database, replacing any existing data in that database with the data from your backup. After restoring the data, it's important to validate that it matches your original source. This involves checking for data integrity, ensuring that no corruption or loss occurred during the backup and restoration process. Regularly performing tests like this not only strengthens your disaster recovery plan, but also instills confidence in your backup procedures. In summary, effective monitoring and backup strategies are non-negotiable components of managing a MongoDB deployment. Consistent monitoring enables you to keep tabs on performance and integrity, while timely backups ensure that you're always prepared for data recovery. By leveraging native tools and possibly advanced solutions available through MongoDB Cloud Manager, you can create a resilient and responsive MongoDB environment, ultimately enhancing the user experience of your applications. Having explored these aspects of database management in MongoDB, you're now better equipped to safeguard your application through best practices in monitoring and backups, ensuring that you can smoothly sail the vibrant seas of data management. Next, we'll dive deeper into the newly integrated features of MongoDB that can further enhance your data handling capabilities. Keep your database healthy, and it will keep your application running optimally. The backbone of any successful database deployment lies in having a solid backup strategy. This principle is pivotal when shaping your MongoDB backup strategy. Today, we'll dive into effective strategies for backing up your MongoDB database to secure your valuable data and ensure you're prepared for any unforeseen catastrophes. So far, we learned about the importance of effective monitoring and backup strategies in managing a MongoDB deployment. Monitoring involves analyzing server behavior and performance metrics, such as memory usage and slow queries, to preemptively address issues. Meanwhile, robust backup methods, including both full and incremental backups, are vital for securing data and ensuring quick recovery. By implementing these practices, we can maintain a resilient and efficient database environment. Now, we will cover comprehensive strategies for effective backups in MongoDB. To create a full backup of your MongoDB database, you can utilize the MongoDump tool, which efficiently captures your data. The command includes the URI option for specifying your database connection string, which contains essential information such as the username, password, host, and part of your MongoDB instance. This allows seamless authentication and access to the specific database you want to back up. The out flag designates the output directory where the backup will be stored. In this case, you should provide a valid path where you want the BSON files, representing your data, to be saved. When you execute the command, it initiates the process of creating a complete dump of your database at that moment, ensuring all data is securely captured. It's important to consider running this backup during off-peak hours to minimize any impact on database performance. After completing the backup, you will find a folder containing BSON files, which can later be used for restoration or analysis as needed. By adhering to this approach, you ensure that you maintain a comprehensive backup strategy for your invaluable data. To create an incremental backup in MongoDB, you will use the MongoDump command with the oplog option. This command is crucial because it leverages MongoDB's operations log, or oplog, which tracks all changes made to the database since the last backup. By specifying oplog, you ensure that the backup not only captures the current state of the database, but also includes any operations that occurred afterward. This feature greatly enhances the backup process, allowing you to manage and secure data changes efficiently without needing to run another full backup. In the provided command, the out flag defines the output directory where your incremental backup will be stored. It's important to choose an organized path for your backups to maintain clarity and ensure you can access them when needed. By running this command, you create a comprehensive snapshot of your MongoDB environment that includes the latest modifications, providing a delicate balance of efficiency and thoroughness as you protect your data over time. To schedule regular backups of your MongoDB database, we utilize a cron job on a Linux system, automating the backup process efficiently. First, by typing crontab e, you open your crontab file, where you can configure scheduled tasks. This command allows you to edit the file and set up your desired cron jobs. The next line you will need to add specifies when and how the backup will occur. Here, the cron expression, 02, instructs the system to run the associated command every day at 2 a.m., an optimal time to minimize interference with your database's performance. The command itself invokes MongoDump, followed by the connection URI that includes your database credentials and specifies the database you wish to backup. Additionally, the out parameter designates the output directory for your backup, where we use a naming convention that appends the current date to the folder name, enhancing organization. This consistency ensures that you maintain a history of backups, allowing easy retrieval if you need to restore your data due to any unforeseen issues. By automating this process, you ensure your data is regularly backed up without manual intervention. Retention policies are another crucial aspect of a complete backup strategy. A well-defined retention policy lets you determine how long you keep each backup before purging it. You wouldn't keep every school project you've ever done forever, would you? So why keep every database backup indefinitely? As your data grows, backups can pile up quickly. A good rule of thumb is to save full backups for a specified number of days, for example, 30 days, and to keep more frequent incremental backups for a shorter time. This encourages you to manage storage effectively while still ensuring that you have access to historical data recovery points. Design your retention policy based on your business needs. Is it critical to retain data for some time? Incorporate this into your backup strategy by using a combination of scripts and cron jobs to delete old backups automatically. To restore a MongoDB database from a backup, the mongostore command is utilized, facilitating the recovery process effectively. This command allows you to specify the database recovery settings through your connection string, which includes the username, password, host, port, and database name, ensuring that you connect to the correct database during restoration. Following this, it's necessary to provide the path to the backup directory where your backup files are located. This structured approach enables you to redefine your database state back to the point when the backup was made, using the BSON files stored within that specified directory. By executing this command, you can effectively recover your data and avoid potential data loss scenarios. After the restoration, it's crucial to review the database carefully to verify that all data is intact and has been restored as expected. Regular tests of the restoration process not only confirm that your backups are functioning correctly, but also bolster your overall data integrity assurance. To secure your backup files, it's essential to encrypt them, and one effective tool for this purpose is GPG. The command provided utilizes GPG to create an encrypted version of your MongoDB backup file, ensuring that sensitive information stays protected from unauthorized access. When you run this command, it prompts you to enter a passphrase, which is a crucial step in the encryption process. This passphrase will be required to decrypt the file later. By encrypting the backup file, you add an additional layer of security. Even if someone gains access to the backup, they won't be able to read the data without the correct passphrase, much like having a diary locked away in a cupboard. Therefore, it is vital to manage your encryption keys securely. Safeguarding these secrets is as critical as the encryption itself. If the keys are lost or compromised, you could permanently lose access to your backup data. Implementing this command as part of your backup strategy not only protects your data, but also reinforces your overall security measures. To effectively secure your local backups, you can utilize the AWS CLI to transfer your backup data to AWS S3, a cloud storage solution that offers robust scalability and security features. The command provided uploads your entire backup directory to a specified S3 bucket, ensuring your data is stored off-site and is safe from local disasters. The AWS S3 CP command is the fundamental part of this operation, where CP signifies that you are copying files. The path to backup is the local path to your backup directory, while S3 / your bucket name / backup directory is the destination you specify in the S3 bucket where your files will be stored. Adding the recursive flag is crucial, as it allows for copying all subdirectories and files within the specified directory, ensuring a complete backup transfer. By leveraging this command consistently, you can automate the backup process, providing peace of mind knowing your data is geographically dispersed and securely stored in the cloud. This practice not only enhances data safety, but also streamlines your backup strategy in a cloud-oriented environment. Finally, remember that a successful backup strategy not only encompasses technical elements, but also requires periodic reviews and updates. As your application complexity grows, so should your backup plans. Make it a habit to revisit your backup strategy regularly. Ensure you communicate with your team about capabilities, expectations, and updates to the policies in place, just like you would about any other critical function of your infrastructure. In summary, an effective backup strategy for MongoDB involves understanding the key types of backups: scheduling, retention policies, testing restorations, securing backup files, leveraging cloud solutions, and continually adjusting your strategy. By implementing these comprehensive practices, you'll bolster your data security and ensure that you are well prepared for any unexpected data issues. With every precaution you take, you safeguard your database's integrity and your application's reliability. So there you have it, backup strategies that not only safeguard your data, but also reinforce overall operational resilience. Remember, a good backup strategy isn't just about participating, it's about creating a safety net that supports everything else. Stay vigilant, stay proactive, and your MongoDB environment will thrive. Atlas Search is an embedded full-text search feature in MongoDB Atlas, created to provide developers with a seamless and scalable way to enhance application functionality through advanced search capabilities. By integrating search directly into MongoDB, Atlas Search eliminates the complexity of managing a separate search system, while offering powerful features that simplify the development of relevance-based applications. So far, we covered the importance of a strategic MongoDB backup solution, including vital components like full and incremental backups. We learned about useful tools such as MongoDump and MongoStar, along with essential scheduling and retention practices for data management. Now, we will delve into Atlas Search, highlighting its key features and architecture, how it operates, and the advantages it brings to MongoDB applications. Atlas Search is built on Apache Lucene, a high-performance search engine library synonymous with reliable and efficient text querying. By leveraging Lucene's strengths, Atlas Search provides users with a robust platform capable of handling complex search requirements effortlessly. What this means is that when you implement Atlas Search in your MongoDB setup, you gain access to a full-text search engine that's not just powerful, but also perfectly integrated into your existing database framework. In this section, we'll examine a practical implementation of a MongoDB Atlas Search query to retrieve relevant documents based on keywords. The code utilizes the aggregation framework, starting with the search stage, which enables full-text searching capabilities directly within your MongoDB collections. Here, the query targets the description field to find documents that contain the phrase MongoDB Atlas Search. This feature highlights the seamless integration of search functionalities without necessitating external systems. Following the search, the code includes a project stage, which is critical for shaping the output of the results. It dictates which fields will be included in the final output, specifically retaining the title and description fields while suppressing the id field for a cleaner display. This design not only simplifies the results returned to the user, but also exemplifies the efficiency and elegance of using Atlas Search for querying relevant information directly from your datasets, reflecting its ease of use and robust capabilities in handling complex search requirements. Another notable feature of Atlas Search is its fuzzy search capability, allowing for the retrieval of relevant results even when there are typos or spelling errors in the search query. This increases user satisfaction, as it compensates for common mistakes people make while typing. For instance, if a user types MongoB instead of MongoDB, the search mechanism can be designed to still find matches, improving the user experience significantly. Atlas Search also supports synonyms. Thus, if users search for a term associated with other phrases, like car versus automobile, it can return results for both terms, enhancing the breadth of search results available to users. Custom scoring enables developers to adjust how results are ranked, allowing for the prioritization of specific content, such as promotional materials or urgent updates. In this example of an Atlas Search query, we leverage the autocomplete feature to enhance user experience by providing dynamic suggestions. The aggregation pipeline begins with the search stage, where we specify that we want to use the autocomplete functionality. By setting the query parameter to Mon, the search is geared towards document titles that start with this string, allowing for a more intuitive search experience. Additionally, the path parameter indicates that the system should look for the term within the title field of the documents. This targeted search ensures that users receive relevant suggestions as they start typing their queries. To refine the results further and prevent overwhelming users with too many options, the query includes a limit stage set to 5. This confines the output to just the top 5 title suggestions, presenting a concise selection for the user to choose from. Overall, this implementation not only showcases the powerful search capabilities of Atlas Search, but also significantly enhances user engagement by facilitating more accurate and meaningful searches. In this section, we will explore how to implement faceting in an Atlas Search query, enhancing the user experience by categorizing search results effectively. The aggregation pipeline begins with a search stage, which executes a search for the term smartphone within the name field of the products collection. This allows users to find relevant products quickly. Following the search, we utilize the facet stage, which serves to group and analyze the search results through different lenses. The first facet, price range, employs the bucket stage to categorize products into defined price ranges, including boundaries like 0 to 200, 200 to 400, and so forth. This aggregation generates a count of how many products fall into each specified price bracket, making it easy for users to compare pricing options. The second facet, ratings, utilizes the group stage, organizing the results by rating and providing a count of how many products correspond to each rating. This dual-faceted approach not only streamlines the search process, but also empowers users to make informed decisions by viewing relevant data segments at a glance. The architecture of Atlas Search is purposefully designed to work seamlessly with MongoDB, eliminating the challenges associated with traditional setups that often require separate systems for search solutions. By incorporating search language and functions directly into the database itself, Atlas Search maintains tight synchronization of data without the inherent latency found in separate search indices. This integration uses a process called MongoDB that operates alongside MongoDB on each node in the cluster, automating efficient search indexing and query handling. This means that every piece of data is synchronized in real time, ensuring that searches return the most up-to-date results. Importantly, this setup negates the traditional complexities and delays caused by external search syncing mechanisms. Once an Atlas Search index is set up for a collection, you can run detailed queries against indexed fields. Each index created can either be dynamically mapped to allow for easy adaptation to schema changes or statically defined for improved performance in well-defined schemas. Creating a search index in MongoDB is a straightforward process that can significantly enhance your application's search capabilities. The command you see here sets up a new search index for the products collection, specifying that 3 fields, name, description, and price, will be indexed for searching. By defining the mappings with dynamic, true, you're ensuring that any future fields added to the documents in this collection will also be automatically indexed, allowing for flexible schema evolution without the need for constant index updates. Indexing these fields improves the performance of search queries, as MongoDB can quickly locate documents based on the specified attributes. This not only simplifies data management, but also enhances the user experience by providing faster search results. Importantly, if changes are needed in the index definition in the future, Atlas Search is capable of rebuilding indexes without interrupting ongoing queries, allowing for seamless updates and continuous availability. This feature highlights the efficiency and robustness of integrating Atlas Search directly within your MongoDB setup. Moreover, Atlas Search includes an analysis of the executed queries, which helps gauge the effectiveness of different search terms and offers insights into how users are engaging with the search features. This reporting functionality enables developers to optimize query performance further and improve user experiences based on collected analytics. With complete visibility over search performance metrics and user interactions, developers can adapt their strategies accordingly, continually enhancing the service provided by their applications. To wrap up, Atlas Search brings significant benefits to MongoDB users by integrating powerful search capabilities seamlessly into their database management. Its features, combined with Apache Lucine's robustness, offer a comprehensive solution for full-text search requirements. Whether it's fuzzy searches, autocomplete, or advanced faceting, Atlas Search provides developers with the tools they need to create engaging and relevant user experiences. In our next session, we will explore how to integrate applications directly with MongoDB effectively. Atlas Search is an advanced embedded full-text search feature in MongoDB Atlas that revolutionizes how developers integrate search capabilities into their applications. Today, we're diving into some of its advanced features that take search functionalities to the next level. So far, we learned about Atlas Search and its key functionalities like fuzzy search, support for synonyms, autocomplete, and faceting. Now we will explore advanced features including advanced query constructs, indexing strategies, and performance optimizations that deepen our understanding of Atlas Search's capabilities. In this section, we will create a search index on the articles collection to enhance our search capabilities. The command createSearchIndex initializes an index named article search, which is crucial for optimizing search efficiency. The index configuration begins with wildcard, signifying our intent to capture all fields for potential searching. This flexibility allows for a broader range of search queries while ensuring that relevant data is indexed. Additionally, we define specific types for indexed fields. In this case, both title and content are designated as type string. This specification is essential as it informs the search engine of how to handle text search appropriately, maximizing relevance and performance. By employing this index, we set the stage for improved query performance, particularly in searches involving large datasets. The structured approach to indexing through this command exemplifies how leveraging Atlas Search can lead to markedly faster and more effective search operations within MongoDB, ultimately enhancing the user experience in applications that rely heavily on dynamic content retrieval. In this aggregation query, we utilize MongoDB's Atlas Search capabilities to execute a complex search using compound queries. The search stage is the first component, where we define a compound query structure. Within this structure, we specify the must condition, indicating that our search should return documents containing the keywords MongoDB Atlas in the title field. The text query is implemented through a straightforward method that matches user search terms effectively. Additionally, the filter clause adds an important layer of precision to our results. Here, we impose a condition that only published articles are included in the findings, which is pivotal for applications like a blog platform where distinguishing between published and unpublished content is necessary. This combination of text and filter queries enhances the search functionality, empowering users to find the most relevant articles based on both keyword relevance and publication status. Overall, this script exemplifies how powerful compound queries can optimize search, results in a user-friendly and efficient manner. In this section, we will explore a query that utilizes Atlas Search's custom scoring feature to enhance the relevance of search results. The query begins by aggregating documents from the articles collection, applying the search operator to perform a full-text search. We specifically look for the phrase advanced features within the content field, which allows us to find all relevant articles containing that exact phrase. However, what sets this query apart is the implementation of custom scoring through the score clause. Here, we introduce a boost on the view count path, assigning it a weight of 2. This means that articles with higher view counts will receive a greater score during the search, making them more likely to appear at the top of the results. This adjustment aligns with user expectations that more popular content should be prioritized, thereby improving the search experience. Overall, this approach not only enhances the search functionality, but also ensures that users are presented with the most relevant and frequently accessed articles first, making your application more effective and user-friendly. In this section, we will explore how to implement facet filtering using MongoDB's aggregation framework, particularly with Atlas Search. The code begins by executing a text search for the term smartphone within the products collection, leveraging the search stage and specifying the use of an index named products index. This allows for efficient searching based on the product name. Following the search, the facet stage is employed to create two distinct segments of results. The first segment groups products by their brand using the group operator, counting the occurrences of each brand to provide an overview of brand distribution within the search results. The second segment uses the bucket operator to categorize products according to price ranges defined by specific boundaries. By grouping products into price brackets, such as $200 and $400, this approach aids users in quickly identifying products within their preferred price ranges. The result of this aggregation pipeline is a comprehensive view that not only presents the products matching the search query, but also segments them into useful categories, enhancing user experience during the shopping process. The following code snippet demonstrates how to implement an autocomplete feature within an online library's search functionality. By utilizing the search stage, the code facilitates real-time suggestions for book titles that begin with a specific string, in this case, ha. This interactive capability is not just user-friendly. It enhances user engagement by providing relevant options as users type, allowing them to refine their searches effortlessly. The autocomplete feature is defined within the search stage, indicating which field to search, here, the title of the books. This means that, as the user enters characters, suggestions will dynamically synchronize with their input, quickly presenting choices that match their intent. To prevent information overload and maintain clarity, the subsequent limit stage restricts the output to the top 5 results. This streamlined approach not only saves time, but also enhances the overall user experience, reducing frustration linked with broader queries. Overall, this code embodies the power of Atlas Search in providing a smooth and responsive search experience, essential for any modern application that values user interaction. As we continue to explore Atlas Search's capabilities, one must highlight the importance of analyzing and optimizing query performance. Atlas Search comes with built-in analytics that helps track how users are interacting with the search functionalities. By monitoring metrics such as search volume and keyword performance, developers are better positioned to adjust their search strategies for maximum engagement. To access this performance insight, one can use a simple query to check the most popular search terms executed in the application context over time. This can guide recruiting content, enhancing SEO strategies, and informing future development efforts. By focusing on logs and analytics, developers can understand which keywords generate high traffic but low conversion. These insights are critical for optimizing search experiences to align with user intent. In this section, we will focus on the command used for backing up your MongoDB deployment, including the critical search indices. The command utilizes MongoDump, a powerful utility that allows administrators to create backups of their MongoDB databases. This specific syntax requires a connection string to your Atlas database, ensuring that the backup operation targets the correct deployment. The gzip option compresses the data during the backup process, making the stored archive more space-efficient. This is particularly valuable when dealing with large databases, as it saves storage costs and speeds up the data transfer. The archive option specifies the name of the output file, which in this case is backup.gz. This file will contain the entire database snapshot, including data and search indices. By executing this command, users can efficiently safeguard their data and search capabilities, facilitating easy restoration if needed. Creating scheduled backups with this command as part of a regular maintenance routine ensures that the integrity of the search functionality is consistently maintained, protecting against potential data loss. In conclusion, Atlas Search provides an impressive suite of features that extend beyond basic full-text search capabilities. From custom scoring to advanced query constructs, autocomplete, and rich analytics, Atlas Search empowers developers to create engaging and relevant search experiences directly within their MongoDB applications. As we wrap up this lesson, you are now equipped with a deeper understanding of how to leverage these advanced features, improving your application's performance, user engagement, and overall search relevance. In our next session, we will shift our focus toward effective application integration with MongoDB, further enhancing our toolkit for building robust database-driven applications. Integrating applications with MongoDB can be a transformative experience for developers and businesses alike, bridging gaps between data storage and application functionality. Today, we're going to explore various methods for integrating applications with MongoDB, including both the native and cloud versions of MongoDB Atlas. By the end of this session, you will have a comprehensive grasp of how to enhance your applications using MongoDB seamlessly. So far, we learned about the advanced features of Atlas Search in MongoDB, including its integration with Apache Lucene, the creation of search indexes, and the use of compound queries. We explored functionalities like custom scoring, facet filtering, and autocomplete, which enhance user engagement and search relevancy. We also discussed the importance of optimizing query performance through analytics and the significance of backup and recovery strategies for search indexes. As we conclude, you now have a comprehensive understanding of how to leverage these features for improved search experiences in applications. Now, we will cover how to integrate applications with MongoDB in various contexts, utilizing tools and frameworks that empower developers. Now that we have our Kubernetes cluster set up, the next step is to add the MongoDB Helm charts repository. This command, helm repo add MongoDB https://mongodb github io/helm charts, connects your Helm installation to the official MongoDB charts, which contain predefined Kubernetes configurations for deploying MongoDB. It's essential for simplifying your installation process and ensuring you have access to the latest updates and features. Following that, we execute the command helm install community operator MongoDB/community operator to install the MongoDB Kubernetes operator. This operator streamlines the management of MongoDB instances directly within the Kubernetes environment by automating tasks like configuration management, upgrades, and scaling. By using this command, we are effectively deploying the operator as a Kubernetes service, enabling us to leverage its capabilities for orchestrating our MongoDB clusters effortlessly. These commands prepare the groundwork for deploying MongoDB instances that can be customized to fit the specific requirements of our applications, enhancing overall efficiency and performance. To deploy a MongoDB instance using the Kubernetes operator, you need to define a YAML configuration that specifies your MongoDB replica set. In the configuration, the API version and kind fields indicate that we're deploying a MongoDB community resource. The metadata section names your MongoDB instance and assigns it to a specific Kubernetes namespace. The spec section is crucial as it outlines the desired state of your MongoDB deployment. Here, we specify members, 3, which indicates that the replica set will consist of 3 MongoDB instances for high availability. The type is set to replica set, ensuring that your MongoDB instances are properly configured to work together. Additionally, we define the MongoDB version, which is specified as 5 in this case. Under Security, authentication is set to use SCRAM, a secure method for user management. In the Users array, we define a user with access rights on the admin database, and we reference the password through a Kubernetes secret for enhanced security. This configuration helps maintain both data integrity and security while enabling you to seamlessly manage your MongoDB instances in a Kubernetes environment. In this section, we'll explore the Terraform configuration for setting up a MongoDB Atlas cluster, which automates the provisioning of your database infrastructure. The first part of the code defines the MongoDB Atlas provider, where you need to input your public and private API keys, creating a secure connection to your MongoDB Atlas account. This setup ensures Terraform can manage your resources by authenticating your requests. Next, the resource block defines the MongoDB Atlas cluster. Here, you specify essential parameters such as the project ID, indicating which project within your Atlas account this cluster belongs to, and the cluster's name. You must also select the cloud provider, in this case, AWS, and define your preferred region for deployment. The configuration highlights important attributes like the number of shards, which is set to 1, ensuring a basic level of scalability, and a replication factor of 3, which guarantees high availability through replicas across multiple servers. Lastly, after saving your configuration in a file named main.tf, you'll initialize the Terraform environment and apply these configurations in the specified files using simple terminal commands, streamlining the entire process of deploying a MongoDB Atlas cluster. In this section, we will examine the example API route created using Next.js to connect to a MongoDB database. The code begins by importing the Mongo client from the MongoDB library, which is essential for establishing a connection to your MongoDB instance. Inside the handler function, the request, rec, and response (res) objects are utilized to process incoming API requests. The Mongo client is instantiated using the connection string stored in an environment variable called MongoDB, ensuring that sensitive data is not hard-coded into your application. Once connected, the database and specific collection are accessed for operations. The code checks the HTTP request method. If it's a POST request, it inserts a new document into the MongoDB collection using the data from the request body. The result of this operation confirms that the document has been added, returning the created object with a 201 status. Conversely, if the method is anything other than POST, it retrieves all documents from the collection and sends them back to the client, returning a 200 status for successful retrieval. Finally, the database connection is closed, ensuring resources are managed correctly. This setup facilitates smooth CRUD operations for your application. To configure Datadog monitoring for your MongoDB database, the primary focus here is on the Datadog agent's configuration file. This YAML configuration uses an init config section followed by an instances definition. In the init config section, we can specify initialization parameters if required, although in this case, it is left empty as there are no specific settings needed for MongoDB integration at this step. The more critical part is the instances section, where you define the MongoDB server connection details. The server attribute contains the connection string, formatted in the standard MongoDB URI syntax. This URI includes the username and password for authentication, along with the address of the MongoDB instance, typically set to localhost when running locally or pointing to your cloud-hosted MongoDB database. By adding this configuration, the Datadog agent will be able to collect metrics directly from the specified MongoDB instance. These metrics include essential performance indicators, such as query response times, memory usage, and connection counts, which will help you monitor the health and efficiency of your database in real time. The result is a robust system for tracking database performance and optimizing resource usage effectively. In this section, we'll focus on creating a webhook using Express in Node.js, which acts as an endpoint to handle incoming requests from MongoDB. The code begins by importing the Express framework and initializing an application instance. The app is set up to parse JSON data using the Express JSON middleware, allowing it to process incoming requests with JSON payloads seamlessly. Next, we define a POST endpoint at /webhook, designed to receive data whenever a specific event occurs in MongoDB, such as the insertion of a new document. When the webhook is triggered, the received data is logged to the console for verification. This step allows developers to see the payload sent from MongoDB, which is crucial for debugging and ensuring that the correct information is being transmitted. After processing the data, the code responds with a status code of 200, indicating that the webhook has been successfully received and processed. Lastly, the application listens on port 3000, making it accessible for incoming requests. This implementation exemplifies how webhooks can facilitate real-time notifications and integrations, enhancing the capabilities of MongoDB within your applications. As we wrap up, integrating applications with MongoDB can elevate your projects to new heights. By utilizing tools like the MongoDB Kubernetes operator, Terraform, Vercel, Datadog, and webhooks, you can create a dynamic and responsive architecture that leverages the strengths of MongoDB's NoSQL database capabilities. This tutorial has walked you through various integration methods, empowering you to harness the full potential of MongoDB. Embrace these tools and watch your applications thrive with real-time data interaction and management efficiency. Happy coding! In this segment, we will examine how to create a new user in MongoDB, which is essential for managing access to your database. The code begins by switching to the admin database, which is necessary since user management functions must be performed in this context. Here, we utilize the DB, create user, function to define a new user named secure user. One notable feature of this code is the use of the prompt password function, which securely captures the user's password input without displaying it on the screen. This prevents unauthorized viewing of sensitive information during the user creation process. The user is assigned a read-write role in the specified database, My Database, granting them the necessary permissions to read from and write to this database. This role-based access control is crucial for managing user permissions effectively, ensuring users have just enough access to perform their tasks without overexposing sensitive data. Overall, this code snippet is a foundational step in establishing secure user authentication within a MongoDB environment. In this section, we will explore the code responsible for authenticating users in MongoDB. The command db auth secure user password is pivotal for verifying a user's credentials against the stored data in the database. When this command is executed, it initiates the authentication process using the Secure Challenge Response Authentication Mechanism, SCRAM, which enhances security by avoiding the transmission of plain text passwords. The db auth function takes two arguments, the username and the password. If the provided credentials match those associated with the user in the database, the authentication is successful, granting access according to the roles assigned to that user. This role-based access control, RBAC, approach ensures that users have permissions that align with their responsibilities, thus reinforcing the security framework within the database. Additionally, this command exemplifies how crucial proper handling of user credentials is in maintaining database integrity and protecting sensitive information from unauthorized access. Understanding and implementing this authentication step is essential for safeguarding the resources and data in any application utilizing MongoDB. In this section, we will configure TLS for secure connections to the MongoDB server, enhancing the security of our authentication process. The configuration begins with specifying the network settings under the Net section of the MongoDB file, where we enable TLS by setting the mode to Require TLS. This setting mandates that all connections to the MongoDB server must be encrypted using TLS, ensuring that data exchanged between the client and server remains secure. Next, we provide the path to the certificate key file, which contains the server's certificate and its associated private key. This is critical as it authenticates the server to clients and enables encrypted communication. Additionally, we specify the CA file, which points to the certificate authority's certificate that issued the server certificate. This verification step confirms that the server's identity is trusted, further safeguarding user credentials during authentication. Together, these configurations ensure that only secure connections are established, critically protecting sensitive data during its transmission across networks. To implement X509 authentication in MongoDB, we first create a user associated with a cryptographic certificate. In this example, the DB create user command is used to define a new user by specifying a distinguished name, DN, within the user field. The DN follows a structured format encompassing various attributes like the common name, CN, organizational unit OU, organization O, locality L, state SD, and country C. This structured identification helps to uniquely recognize the user in a high-security environment. The user is granted a read-write role on a specified database, my database, allowing them to perform read and write operations within that context. This role-based access control ensures that users have the necessary permissions tailored to their needs, which is fundamental for maintaining security and data integrity. When the user wants to authenticate, they will use a command that utilizes TLS for a secure connection. This command specifies the paths to the client certificate and the certificate authority, CA file, the authentication database as external, and the mechanism as MongoDB X509. This approach enhances security by negating the need for passwords and reducing the risk of password compromise, relying instead on robust cryptographic certificates for authentication. In this section, we're focusing on creating a custom role in MongoDB to manage user permissions effectively. The script begins by switching to the admin database, which is essential because user roles and permissions are typically defined at the administrative level in MongoDB. Next, we create a user-defined role called read and insert. This role has specific privileges granted to it, allowing its assigned users to perform the find and insert operations on data within the My Database. By clearly defining these actions in the privileges array, we ensure that users with this role cannot execute operations like modifying or deleting documents, thereby adhering to the principle of least privilege. This approach empowers database administrators to enforce strict access controls, only allowing users the minimum permissions necessary for their tasks. Overall, this setup not only enhances security within the database, but also aligns with best practices for role management in user authentication processes. In this section, we focus on enhancing security by defining user roles with specific connection restrictions in MongoDB. The code snippet illustrates the creation of a custom role named Restricted User, which is designed to limit authentication to select client IP addresses and specific server addresses. The authentication restrictions field is a key feature of this role, allowing us to specify which client IPs can connect to the MongoDB server. In this example, only clients originating from the IP addresses 192.168.1.1 and 192.168.1.2 are permitted to authenticate. Additionally, the role restricts access to only the server at the IP address 192.168.1.100. This means that even if a user has valid credentials, they will only be able to connect if they are coming from the allowed IPs and server. By implementing such restrictions, we create a robust security layer that significantly reduces the potential for unauthorized access and breaches. This practice not only helps protect sensitive data, but also enforces tighter control over who can interact with the MongoDB environment. Such measures are vital in maintaining a secure database management system. As we wrap up our discussion on online safety and user authentication, remember to combine these best practices. Educate users on password hygiene, promote multi-factor authentication, and continuously monitor for suspicious activities. In conclusion, we've covered crucial tips for security in online environments, particularly authenticating users in database systems like MongoDB. We discussed various methods, from password-based to certificate-based authentication, emphasizing the need for secure connections and role-based access management. Ensuring robust online security is an ongoing effort. As threats evolve, so must our strategies to counteract those risks effectively. Stay vigilant, keep learning, and apply these practices to protect not just data, but the identities tied to them. Thank you for joining this session on security tips for online safety. Auditing in MongoDB is a critical aspect of ensuring security and compliance within your database systems. It allows administrators to monitor specific activities, providing a detailed view of operations relevant to business and data security. By enabling auditing, organizations can achieve a higher level of oversight on data modifications, management operations, and user authentication events. This process not only helps in identifying unauthorized access, but also supports regulatory compliance and accountability, making it an indispensable tool in today's data-driven environments. So far, we covered the importance of online safety and user authentication for securing access to database systems like MongoDB. We explored various authentication methods, including passwords, multi-factor authentication, and X509 certificates, emphasizing secure connections with TLS. Additionally, we discussed role-based access control to manage user privileges effectively and the significance of monitoring for suspicious activities. Now, we will discuss the intricate world of auditing in MongoDB, focusing on configuration, implementation strategies, and how to make the most of the auditing features to bolster your database security. To configure auditing in your MongoDB instance, you'll need to adjust the mongodconf file, which controls various operational settings. In this setup, the storage section defines the database storage options, where dbpath specifies the directory for storing your database files. Notably, the audit log subsection is crucial for enabling audit logging. By setting the destination to File, you instruct MongoDB to write audit logs directly to a file, ensuring that logs are stored persistently for later review. The Format option, set to JSON, allows for structured logging, making it easier to parse and analyze the data using various tools. Lastly, the path parameter designates the exact location of the audit log file, providing a clear and accessible place for administrators to find and utilize the logs for monitoring compliance and security oversight. This configuration is foundational to efficiently leveraging MongoDB's auditing capabilities and enhancing oversight of database activities. To implement a targeted auditing strategy, we utilize a JSON filter that specifies the criteria for logged events. In this structure, the Users field identifies the user for whom we want to audit actions, in this case, Alice, and the database is designated as admin. The A-type key defines the type of operations we are interested in monitoring. Here, we focus on insert actions, which allows us to capture every instance where Alice adds data to the database. The params NS field specifies the namespace of the collection we are auditing, formatted as myDatabaseMyCollection. This is crucial because it confines our audit logs to only those insert operations that occur within this particular collection, ensuring we collect data that is both relevant and manageable. By utilizing this audit filter, administrators can streamline their logging process, which minimizes information overload and enhances clarity in the audit trails, allowing for precise tracking of significant user actions. This meticulous approach helps maintain security and compliance standards within the database environment. To effectively track modifications in your healthcare information management system, you can implement a targeted audit filter. This particular JSON structure helps you specify exactly what actions you want to log within the patient records collection of your MongoDB database. The key component here is the params NS field, which identifies the namespace of the collection. In this case, it specifies healthcare patient records. This allows you to focus exclusively on this collection for auditing purposes. The A-type field, defined with an array, employs the in operator to capture all critical data modification actions, inserts, updates, and deletes. By doing this, you ensure that every change made within the patient records collection is logged, providing a comprehensive audit trail. This configuration is fundamental for compliance with regulations like HIPAA, as it empowers administrators to monitor access and alterations to sensitive patient information effectively. With such an audit filter in place, you gain insight into how the data is handled, enhancing both security and accountability within your system. In the context of maintaining a healthy audit logging system within MongoDB, the command used is critical for efficient log management. The command db, admin command, log rotate, audit, triggers the rotation of audit logs in your MongoDB instance. This means that the system will handle the current audit logs by closing off the current log and starting a new one, thereby preventing the accumulation of excessive data in a single log file. Rotating logs is essential in managing disk space and ensuring that the database performance remains optimal, especially for organizations that must adhere to compliance standards like HIPAA, which dictate log retention durations. By automating this log rotation process, administrators reduce the risk of manual errors and help maintain compliance without the constant need for supervision. Additionally, executing this command periodically can help ensure continuous monitoring and systematic cleanup of any outdated logs, which is crucial for both security and operational efficiency in a data-driven environment. In this section, we will explore a Python script designed to parse JSON audit logs, specifically filtering and displaying actions performed by a user named Alice. The code begins by importing the JSON module, allowing us to read and manipulate JSON data easily. The primary function, readAuditLog, takes a single parameter, file path, which specifies the location of the audit log file. It then opens this file and loads its contents into a variable called logs, enabling us to work with the data in a structured format. Inside a loop, the script iterates through each log entry, systematically checking if the username Alice exists in the records. This conditional check looks at the users field within each log entry, specifically targeting the first user in the list. If a match is found, the script extracts and prints out key information, such as the type of action taken, represented by the A-type field, and the timestamp of that action from the TS field. This functionality provides valuable insights into user behavior, making it easier to monitor and audit activities performed by specific users within the database. As we know, monitoring for suspicious activity is a vital part of an effective auditing strategy. Setting up alerts for specific actions can facilitate proactive responses to any unauthorized access attempts. Tools like Splunk can aggregate and analyze your audit logs, offering the ability to apply real-time analysis and alerting functions based on predefined criteria. Implementing alerts can also be done through configuring MongoDB's internal processes. By utilizing the monitoring and alert features in your MongoDB Atlas instance for M10 clusters and above, administrators can create rules for specific actions that trigger notifications. For instance, when a user accesses sensitive data, administrators can receive alerts immediately, allowing for a quick investigation. As we wrap up our exploration of auditing in MongoDB, it's essential to remember that this feature is not just a technical capability. It's a fundamental component of your overall database security strategy. The insights gained through robust auditing can enhance compliance with legal requirements and improve the management of sensitive data while fostering accountability within your organization. Implementing such systems may seem daunting initially, but taking a methodical approach to configuration, filter setup, and log analysis can bring clarity and security to your database practices. With the right governance around MongoDB auditing, you not only increase safety, but also instill confidence among your users and stakeholders in the integrity of your data management processes. So far, we've discussed how auditing in MongoDB plays a crucial role in tracking database activities relevant to security and compliance. We've covered its configuration, including capturing specific actions and monitoring user behavior. Now, make sure you take these insights and implement them in your system to ensure that your data remains protected and compliant with necessary regulations. Thank you for joining me in this tutorial. Sure, here is the original video, script on the topic of comprehensive data encryption in MongoDB. In the digital age, protecting sensitive data is not just a matter of best practice, it's crucial. Today, we're diving deep into how MongoDB offers comprehensive data encryption capabilities to secure your database. Specifically, we'll take a look at 3 primary types of encryption: encryption at rest, encryption in transit, and client-side field level encryption. So far, we have learned about the significance of auditing in MongoDB to ensure security and compliance through diligent tracking of user actions and database activities. We configured audit processes to capture vital actions and discuss the importance of customizing audit filters to prevent information overload. We explored how maintaining audit logs and utilizing analysis tools can greatly enhance security. Now, we will talk about how MongoDB uses encryption to protect the data stored in its systems. To generate a master encryption key for MongoDB, we use OpenSSL, a powerful tool for securing data. The command openSLRAND base32 path to your MongoDB key file creates a random 256-bit key encoded in base64 and saves it to a specified file. This key is crucial for encrypting and decrypting other data keys in MongoDB, acting as the foundation of your database's security. After generating the key, it's important to set the appropriate file permissions using chmod 600 path to your MongoDB key file. This command restricts access to the key file, allowing only the owner read and write privileges. Such measures help prevent unauthorized users from accessing or modifying sensitive encryption keys, thus enhancing the overall security of your data. Together, these steps secure the master key, ensuring that even if someone gains physical access to the file system, they cannot access the encryption keys that protect your stored data. To enable encryption at rest in MongoDB, you must modify your MongoDB configuration file. The code snippet specifies 2 key settings under the security section. The first is Enable Encryption, which is set to true to activate encryption for data stored on disk. This ensures that all data will be encrypted and protected from unauthorized access, supporting compliance with various regulations. The second setting, Encryption Key File, points to the path of your key file, which contains the master encryption key used to encrypt and decrypt the data stored in the database. It's crucial to ensure that this key file is securely managed, as losing it could make the encrypted data impossible to access. After making these changes, remember to restart the MongoDB service to apply the configuration. By completing this setup, you effectively turn on a protective layer for your data, ensuring that even if a potential attacker gains physical access, the information remains secure and unintelligible. To enhance the security of your encryption keys, you can configure MongoDB to integrate with an external key management service, KMS. In this code configuration, the security settings are adjusted to enable encryption while specifying parameters for the KMS. The Enable Encryption parameter is set to true, which activates encryption in the MongoDB instance. The KMIP subsection details the connection to your KMS, allowing MongoDB to retrieve and manage encryption keys securely. The key identifier represents the unique identifier for a specific key stored in the KMS, while server name specifies the address of the KMS server MongoDB will connect to. Additionally, the server CA file parameter refers to the file path containing the certificate authority. CA, certificate, used to verify the server's identity, ensuring secure communication. The client certificate file and client private key file paths are used for client authentication, allowing the MongoDB instance to prove its identity to the KMS. By utilizing this configuration, MongoDB ensures that encryption keys are managed with a high level of security, making it a recommended practice for secure production environments. To implement TLS encryption for your MongoDB instance, you will need to configure specific settings in your MongoDB configuration file. This code snippet allows you to establish a secure connection through the Transport Layer Security (TLS) protocol. The first line specifies the network configuration under the section labeled Net. Within this section, the TLS setting is introduced, indicating that TLS configurations will follow. The mode, Require TLS line is particularly crucial, as it mandates that all clients connecting to this MongoDB server must use TLS for secure communication. This ensures that any data transmitted over the network is encrypted, protecting it from potential eavesdroppers. Next, the configuration points to the certificate key file, which should contain your SSL certificate and private key. This file is critical as it authenticates the server and establishes a secured channel for client communication. Finally, the CAR file parameter specifies the path to your certificate authorities file. This file validates the authenticity of the certificate used by the server, preventing man-in-the-middle attacks and ensuring that clients can verify the server's identity. Together, these settings create a robust framework for secure data transmission within your MongoDB environment. It's also worth mentioning that if you're using MongoDB Atlas, network encryption is enabled by default, so you're covered right out of the box. However, if you're configuring on-premises systems, you have flexibility in your TLS setup. You can use options like Require TLS, Prefer TLS, Allow TLS, or even disable it altogether, though I wouldn't recommend the last option. The Require TLS mode is the strictest, as it demands all clients use TLS encryption, while Prefer TLS allows for some flexibility if TLS isn't available. In this section, we are configuring TLS, Transport Layer Security, for our MongoDB setup to ensure secure connections. The configuration begins with the TLS option, where we set the mode to Require TLS, which is essential for enforcing encryption when clients connect to the MongoDB instance. This means that all incoming connections must use TLS, adding a robust layer of security. Next, we specify the certificate key file, which points to the file containing both the server certificate and its corresponding private key. This file is crucial for establishing a secure encrypted connection between clients and the MongoDB server. Additionally, we include the CAR file, which references the certificate authority, CA, that issued the server certificate. This CA file plays a vital role in client authentication by ensuring that the clients can verify the server's identity, helping to prevent man-in-the-middle attacks. Together, these configurations empower MongoDB to encrypt data transmitted over the network, enhance user authentication, and maintain the overall integrity of the database connections. This is an essential practice for protecting sensitive information during transit. In this snippet, we implement Client-Side Field Level Encryption, CSFLE, using PyMongo to secure sensitive data before it reaches the database. First, the master key is defined for local key management, which lays the foundation for encrypting and decrypting your data. The KMS provider's dictionary specifies that we are using local key management, ensuring that the encryption keys remain within your control. Next, we create a schema map, where you'll define which fields in your documents should be encrypted, thereby customizing the encryption to suit your application's needs. This allows for specified fields to be automatically encrypted according to your defined schema. Then we configure auto-encryption ops, which takes the KMS providers and schema map along with the key vault namespace, where the keys will be stored in MongoDB. Finally, we instantiate a Mongo client with these auto-encryption options. By doing this, any data that is sent to the database will have the specified fields encrypted on the client side, ensuring that sensitive data remains secure even in the event of a database breach. The beauty of CSFLE lies in its automatic handling of encryption keys. When creating documents, MongoDB will automatically encrypt specified fields before they are sent to the database. When retrieving documents, the client can seamlessly access the original data without needing to manually decrypt. This capability means that developers can focus on the business logic, while MongoDB manages security behind the scenes. Plus, even if the database server is compromised, the actual sensitive data remains encrypted, protecting against data breaches. However, there are considerations when implementing CSFLE. Performance can be affected due to the overhead of encryption operations. Thus, understanding the specific fields that require encryption and the impact of encryption levels is crucial for maintaining responsiveness in your application. You must also carefully manage your encryption keys. Losing the master key could render all encrypted data inaccessible, so it is paramount to have robust key management and backup procedures in place. To summarize, we've covered how MongoDB provides powerful encryption features that keep your data secure at rest, in transit, and at the field level with CSFLE. This comprehensive approach to data encryption not only enhances security, but also helps comply with regulatory requirements. As we navigate the challenges of data privacy and security, understanding these tools is imperative for any organization looking to safeguard their sensitive information. MongoDB's encryption capabilities empower developers and can be tailored to fit a wide variety of application needs. Thank you for joining me today. I hope you now have a deeper understanding of data encryption in MongoDB and feel more confident in implementing these features in your projects. Remember, secure your data and happy coding.